Give me 1 second to reconnect here as well. There is the Zoom link. Okay, I think we are back in action. No, that was not the. Yep. Slideshow. Perfect. Okay, we're back again. Great. Okay, sorry about that. Yeah, so yeah, between working on sort of the Ross core team at Willow Garage, yeah, as mentioned, sort of worked at several different companies, Suitable Technologies. Actually, the Beam robot, I think I noticed we actually still have one outside. If you sort of walk down the hall that way, you'll see a Beam, one of these Beam telepresence robots in the hallway down here. So I guess that's been around now for 12, 13 years. They're still in use, which is pretty exciting. But so I want to talk about sort of what is Rerun. So Rerun is an open source SDK and visualization tool built in Rust. We have APIs in Rust, Python, C++. These APIs are in general language bindings implemented on top of the Rust core. This will sort of be a recurring story through this. Actually, I think I could just move this. Nope, I'm stuck with this here. Okay. There we go. Okay, we'll take that. And the data model of sort of Rerun is sort of from the ground up built for robotic style data. Sometimes we'll call this multimodal data, physical AI data, right? This is sort of, we have data primitives for 2D, 3D geometries, transforms, projections, images, videos, point clouds, of all the kinds of data that you would typically see in robotic systems. In terms of sort of how you go about using Rerun, you sort of model that data in Rerun via log call. Sort of you describe the semantics of your data, you sort of send it into the data system, and then you use that in a couple different ways. You either take that data and visualize it in the Rerun viewer, or you work with that data via queries that pull that data back out of the Rerun system. Sort of what I sort of want to show here, sort of like high level view of sort of like how the Rerun architecture is set up. In general, you have sort of this user space code with the bindings on top of the Rust core that's sort of taking care of taking their data, sending it across the gRPC interface into the viewer or into the storage system. That same interface can be used to query things back again, but there's sort of a lot of flexibility in terms of the different ways that you can configure the system, right? You can route the data, to file. You can load it, implement plugins to load data from different file formats into the viewer, into these systems, configure the layout of the viewers, sort of, et cetera, et cetera. If I've got time, I'll sort of get more into that in a little bit, but I'm gonna actually just quickly here show a live demo of the viewer, just to kind of, I think this gives sort of people a better sense of like what the viewer is and how it works if you haven't seen it before. So this is, I don't know if folks are familiar with the new scenes, sort of open source or open data set. This is sort of that data set converted into the rerun format. You can see sort of some of that multimodal data that I was talking about. We've got our point cloud data. We've got cameras that have been sort of transformed according to their extrinsics. We've got sort of the camera feeds down in here. All of this data, these 3D annotations in world space are actually being projected into these camera images using the camera calibration and the extrinsics of that system. If I mouse over these annotations, I can sort of see the data. I can see that this is an object that's been annotated as a barrier, for example. I can select this, come back out. Sort of all this data is connected. I can see this is the one that I selected in that camera view. It's still selected here in the top level 3D view. So everything's connected. And everything is indexed temporally over time, right? And so I can come here and I can change, sort of change the timeline, scrub back and forth in real time. That's, I think, the bulk of what I wanted to show here. Sort of another, even less time spent on this one. Another example, but just we also support just scalar time series data, as well. Similar kind of setup. Scrub back and forth, see your data, inspect the signals, sort of understand what is going on there. And so I think the reason that we're here. Let me go back to slideshow mode. Right. So rerun is built in Rust. Right. This was a core company decision from the very beginning. I think one of our co-founders, Emil, wrote a blog post back in 2022, maybe, about sort of like why we chose to build rerun in Rust. In general, I feel like most of those reasons, I think, are the same reasons that you'll see in sort of any post about why is Rust good for just general software engineering, right? It's fast, it's safe, it's cross-platform. You can run it in web, right? I was able to show those demos in the browser here on this random conference laptop instead of needing to connect to my laptop here. I didn't need to install anything to do that. It's got great tooling, right? A really big notable thing for us, and sort of in conjunction with this portability story that's important, is that we have a single stack for all of our developers at Rerun. Right? We don't have a front-end team that's working with JavaScript and a back-end team that's working in C++, and the inability of engineers to sort of like navigate that stack. And anyone is sort of working in sort of the same language, same constructs across that entire code base, and that actually ends up being quite beneficial for us as well. And then Rerun is also it's built on a Rust foundation, right? We didn't build the whole thing from scratch. There's a lot of these sort of powerful, open source building blocks in the Rust ecosystem, any one of which would have been kind of a huge undertaking for us to tackle. And sort of run through these, somewhat quickly. But eGUI is, sort of a fairly common Rust GUI framework. It's actually developed by our co-founder Emil, and we're sort of using Rerun as an opportunity to push the eGUI project itself forward as well. WGPU is we sort of use for rendering. WebSys and WASM BindGen for sticking stuff in the browser and sort of navigating those JavaScript bindings. IO3 is how we manage our Python bindings. On top of that Rust core, it makes it sort of very easy to build these sort of ergonomic bidirectional Python into Rust back into Python, which is, I think, increasingly important with this sort of like robotics needing to do a lot of Python in this ML world where everyone is using PyTorch these days for things. ArrowRS and Data Fusion. ArrowRS is the data format we build on top of. Data Fusion is a full query engine written in Rust that's extensible, and Lance is a columnar on disk format. It supports fast vector index support that we're using for some things as well. And then hundreds more libraries, smaller libraries, transitive dependencies that we're sort of building on top of here. In terms of actual spotlights of why Rust is also just great for robotics, there were two things that jumped out to me when I was sort of thinking about Rerun and sort of drawing some analogies. Like we're a tool for understanding robotics data, but we do have some of the same challenges that you see in actual robotics systems, right? So for Rerun, application responsiveness is critical to usability of the system, right? We want that mouse movement to render update loop to be as tight as possible. in most robotic applications, you have a very similar kind of like closed loop control constraint, right? Sensor input to control output latency is critical to control performance in most contexts. And so, Rust really sort of shines here in terms of, clear and explicit heap usage, preventing us from needing to have allocations like inside the inner loop here, deterministic drop semantics, sort of avoiding ill-timed garbage collections, lifetime tracking, borrow checking, make it sort of easy to sort of safely access read-only data structures without race conditions and locks. And then the compiler in general is just high performance, right? Just make things faster and it's easier to close a control loop. And then safety, right? So rerun, right, as a library that we're asking others to incorporate into their program. Like, we never want to be responsible for crashing someone else's software. And in many cases, you're using like this software to collect like valuable data that you don't want to lose. Again, we don't want to crash and lose someone's data. Robotics, very, similar, I would say probably even higher stakes, right? You don't want to, if software in your robot crashes, your risk of like physical damage or other safety concerns is high. And, Rust, again, just really shines here with, explicit error handling, enums, match statements, just sort of force handling of edge conditions more effectively. And the borrow checker and lifetime tracking, like in general, avoids many classes of like the classic C++ segmentation fault, null pointer, dereferencing, like these things that plague many C++ code bases are. I'm not going to say they're non-existent, but they're much rarer in Rust code bases, right? And you can still write unsafe code in Rust, but like the unsafe unsafe annotation where you're writing your unsafe code really lets us like focus the scrutiny where that scrutiny belongs and not spreading that scrutiny out into other code that you can trust to be like generally safe based on the design of the language in general. So the thing I want to kind of really get into here is that like Rust enables rerun among all these other like nice things, rerun to be flexible, and this flexibility has like two aspects that I think are equally important. So one is like it's flexible in what you can do with it, right? Extensible, composable data type handling, generic inspection of arrow data. Rust makes all of these kinds of things, again, easy with sort of enums, match statements, sort of play a role in like ergonomic handling of these complex data structures. Rust traits really provide, I think, a nice extensibility story that's preferable to sort of my prior experiences extending things in C++. So I've got a couple code examples that are probably too small for folks to see here easily, but like using match statement to process an image buffer and make sure you're handling the different the different permutations of color model and data type and aligning your buffers there. Narrowing data types were sort of necessary here for mapping some stuff to WGPU. And the trait system, right, is in rerun, especially in Rust, if you have a native type you want to log with rerun, right, you just implement the rerun loggable trait on that type, and now you can log it. You don't need to like go and subclass that type or duck type things without sort of the support of a compiler, as you sort of might end up doing in Python. And then Rust enables rerun to be like flexible in terms of where and how you can use it, right? So we have an SDK in Rust, C++, Python, running on Linux, Mac, Windows, x86, ARM, all of these different contexts. The viewer is available sort of both native and in web application context, or embedded in an IPython notebook. And so it's just like the general Rust story of like write something once, run it everywhere, just like really opens up this opportunity to have a single maintainable code base that you're using all over the place in this complex stack. And sort of like why is this flexibility important now, right? Right, I really think that like the application of ML to robotics and sort of everything that's been happening, maybe the past 2 years, sort of in particular, I think that it started much before that, but I think we've really seen sort of a recent explosion of like what is the nature of a robotic stack, right? And so if we think of like classic robotic stack, right, like back when I was working on ROS, at Willow Garage, it was like, okay, you've got complex control inference software running in some kind of robot framework, and you want to, the emphasis there is testing, validating, sort of either on the robot or in simulation. But a lot of this, like the same pattern of like record the messages that are being passed around on the robot, and then replay those native messages, in some other framework and validate that they're doing what you want to do. And you just keep repeating that loop until the robot sort of does what it is that you want it to do. And sort of like by contrast, right, these ML-based robotic stacks that I assume we'll be talking some more about that like here and certainly across ICRA. I've seen several several talks that are going to be talking about different aspects of this, but right, we sort of depend on models that are trained somehow using collected data, right? So there's this like big emphasis on data collection, curation, training, model validation, and these workflows, like they don't use that kind of like record and replay centric model in the same way. They tend to use different tools and frameworks, a very heavy Python influence. Model training frequently necessitates like this like cloud scale infra, which means you've moved your data somewhere else. It's not, not on your robot or in your lab anymore. It's in a cloud somewhere in this aspect of like, oh, we can access that data, remotely. I want to view it in a browser context where like these like remote access things make sense. Just kind of like help with that in general. And then, lastly, like many of these like ML pipelines depend on data being structured in sort of this tabular rather than sort of message stream oriented format. And right, so to that end, parts of rerun can be used across that full stack. So we have like, again, one code base, and we're using that code base in the context of like logging source data on the robot. We're using that for generating visualizations and a local, high performance native viewer running natively where it has access to your like full GPU and all the RAM on your system. You can do much deeper, data exploration there, but also, processing and indexing in the storage engine, ad hoc queries, again, written in a IPython notebook, or sort of transforming data as part of like query execution within Data Fusion as either part of like analytics jobs or these training jobs. And then sort of the core of what we're doing, right, in all of these different like contexts where we're sort of excited about running rerun, like comes down to converting data, from one form to another, right? So, it's like, a couple examples of this, like, in logging, log calls are converting data from some runtime data format to like a canonical rerun representation. In the viewer, we're taking that canonical representation and we're transforming it in some way into graphics primitives that we can send to the GPU and use for sort of visualizing this data, or transforming data to like align things that are sampled on different timelines, align them, normalize them into these data frame oriented representations that are needed by the sort of the modern ML pipelines. Right, in the course of doing this, there's many different types of conversions that we need to do. We're doing, temporal sampling and alignment, or spatial sampling and filtering, or these geometric conversions, rotations, translation, scale changes, projections, just general data format conversions. I want to take JPEG encoded data or video data and convert it into an image buffer, that's an actual dense pixel buffer, or just other general signal processing functions, right? And if we were to take all of these different conversions and implement all of those in Rust, and then implement them again in Python and again in C++, and make sure that the optimizations are appropriate on both Windows and Mac, and sort of like maintaining that would just be sort of totally impractical without this sort of facility of Rust to sort of have, okay, no, we've got one core, and we can just take that core and embed it in all of these different contexts and use these same implemented data transforms across all those different places. And so, in order to facilitate this, right, so the canonical data format that we use sort of inside of rerun is based on Apache Arrow. Apache Arrow is a sort of a language agnostic columnar format, provides a structured memory layout across processes, libraries, and languages. And I find sort of it generally plays very nicely with Rust, and in this regard. So you have like these like contiguous cache-friendly buffers that can be passed around, zero copy, into different contexts. Sort of just like Rust is embeddable in all of these different contexts, Arrow is sort of set up to work natively in these different contexts. So we can sort of easily do things like allocate an Arrow buffer from native Python code, or take the buffer in, say, a pandas data frame, and we can efficiently get that across the FFI boundary into Rust and work with that data in that same format. And right, so like Arrow has been, I think, gaining traction in sort of what I would call these like other data ecosystem projects: Pandas, Spark, Data Fusion, Lance, Polars, DuckDB, ClickHouse. Right, if you can get your data into Arrow, it's significantly easier to work with these other sort of data ecosystem tools. And sort of in the sort of in the context of then using that Arrow data for these data type conversions and transformations that that I was talking about, right? The like Arrow format breaks data up into units of record batch. So a record batch is like the minimum sort of packet that contains multiple columns of the same logical length. It has buffers within those columns are guaranteed to be contiguous in memory, and this sort of makes this an ideal unit for implementing these transformation kernels. And so like we can think of like all of those different data transformations that I was talking about a second ago as really just like functional operations over these record batches, right? So I take some number of arrays as an input and I produce some number of arrays as an output, and we can take that core kernel and we can implement it once in Rust, and we can use it safely and performantly and efficiently in all of these different contexts, right? As long as we've like gotten the data into the right structure, now we can run that code in the context where we need it and do the transformation that we need to do. And then sort of lastly, as I'm sort of selling Arrow here a bit, is like, oh, put all your data in Arrow. It'll be great. You can do everything, and do all that stuff in Rust. Like there's still like a little bit of a challenge here, which is that Arrow is like great for generically and portably defining what I'm calling sort of like physical data types. So something like a fixed size list of fixed size list array. So this is an array made up of an internal fixed size list of 4 elements that are float 32, right? And you can say, okay, that's great. I know how to access that memory. I can do stuff with it, but like, what is actually that data? And Arrow doesn't give us sort of tools for doing that. So Rerun sort of extends Arrow very lightly using the Arrow metadata system to track semantic meaning, right? So you can assign, this 4 element, float is it's a rotation that represents a quaternion that represents a rotation, or it's actually a color that represents an RGBA value, right? And so you don't want to try to rotate a point in space using a color, right? That doesn't, I mean, I guess it makes sense in some sense if you're doing, different kinds of like color space operations, but if you're thinking that as like a geometric rotation, you don't want to like misinterpret it as something different. You definitely don't want to view your quaternions, right, as colors, to like colorize a point cloud. And right, so these semantic annotations enable sort of better default visualizations, and just like within these like kernels that these transformation kernels that we implement, correct application of these data transformations. With the interruption, I lost track of where we are time-wise. How much time do I have, if any? 10 minutes. Oh, fantastic. Okay. And then, so I guess, yeah, in summary, right, ML-based robotic stacks sort of make it more important than ever to like access and transform data like across like a broad variety of different contexts. Rust, like in general, lets Rerun leverage this like single one code base to do this portably while maintaining sort of high performance and safety everywhere. Many aspects of the Rust language in general are particularly well suited for the task of processing data from arbitrary external sources. And Apache Arrow helps sort of with the task of like moving data between these different contexts, keeping track of like what that data is, and sort of efficiently doing these transformations. So with that, I'm going to show one more demo here, hopefully. I'm going to have to share from my laptop instead. Screen, entire screen. Okay, cool. I make this. That's a little bit better. Perfect. Let me come back here. This is mirroring. Perfect. Okay. Let me come back to the beginning of this notebook. Right. So this is, kind of an example of using rerun, kind of in that context that I was just describing of, okay, we've got some robotics data, we captured it, we modeled it, we send it into rerun, and now we want to sort of do something, something with this. And so this is a Jupyter notebook, and I'm running, I guess, locally on this laptop because I wasn't sure what the Wi-Fi situation was going to be here. A copy of our soon to be released data platform product as well. So not everything here can be done totally with the open source project, but a lot of it still sort of works with that same rerun core. So I'm gonna start this notebook off, and let's just initialize here, right? So I can see I've connected to a server here. I have this, I'm using the Droid data set, which some of you I'm sure are familiar with. And so I have I think just 50 episodes from the Droid data set here, sort of accessible in this catalog, and I can open one of these, and right, I'm right here. I'm in a Jupyter notebook, but I have a copy of the rerun viewer embedded as a cell in the notebook. I'm able to do this again, all because the rerun viewer is cross-platform. I can compile it to WASM, and I can stick it places like a Jupyter notebook. So you can just do these things in line, which is quite convenient. Double click on what? That worked? Okay, cool. Awesome. And right, so I've got there we go. I've got my URDF loaded model. I've got some scalar values for my joint angles, gripper position. I've got video feeds from the different cameras, from that Droid data set. I'll note here, right? This is just the kinds of things that it's just nice to be able to do, right? This is video encoded data being decoded into images, in the browser. I'm not having to like decode those into full images and send those across the wire somewhere to get to rerun. And so I can just sort of do normal. I want to review this data. I want to understand what's happening here. Right, then I can sort of in Python SDK. This is Python calling through to a Rust library under the hood. Take care of all this stuff. I can get access to the same representation of that catalog that we saw before, but now I'm getting it as a data fusion data frame, back in Python land, right? So I can use that data. I can get a URL that that points to that data, and I can if I wanted to just open that individual recording up directly, I can still do that again. Back, okay, just open this data, show me this data in the notebook. And I want to actually do something more data sciencey, data sciencey as being like a prerequisite to more of like the ML type work. Again, here, so I can as I was describing these like APIs for querying stuff, I can actually bump this a little bit. Run a query. I'm going to sort of do this data frame query view on top of the episode data, and I just want to look at the contents in this this namespace, robot /*, and I want to get that back as a data frame. And now I want to take this and I'm going to filter it down to just the first episode. I'm going to limit it. I'm going to look a little bit further into that episode and just get 20 results here. And so I'm taking that that same data. I'm transforming that data. Using rerun, binding this into data fusion, passing the data through, and getting it back sort of in this tabular representation that's a little bit more useful for some of these other contexts. Right? This is something that no longer looks like ROS messages in a ROS bag, right? It looks much more like the kind of data frame that you might want to use in a context like working with PyTorch. And we can do other stuff with this data now that we have it in this form. So this is sort of an example of writing for every episode, I want to count the gripper position, the number of like frames where the gripper position was greater than a threshold of 0.3. And I'm going to aggregate those over partition ID, and I'm going to end up with a table at the end of that process. And I'm actually going to add a cell here. I could look at that table here, right, and just in the notebook directly as like a data frame view. But again, this table is Apache Arrow data under the hood. I can take that Arrow data and I can send it back to the rerun viewer, because that's sort of what this is all designed to do, right? So rerun viewer also now ends up being kind of a data frame viewer that's able to look at the same data sources in addition to the other kinds of data sets we were looking at earlier, right? So that compute operation that I just ran, right? I wanted a grip time, right? I look at the shortest grip time here. I can open this again directly through the viewer. I can see, oh yeah, this is a data set or an episode where the gripper was closed for a relatively short amount of time. I can come back here, I can scroll down, I can pick one of these longer ones, right? This is sort of the operation that we wanted. This is sort of help me find episodes where some particular criteria was met, according to the data that I'm interested in. And then I can do sort of a similar operation here. Vector search. I can build up a vector index. I happen to have an embedding vector in that data set that we computed on sort of every image when we were sort of loading it in. I'm just going to I picked sort of a random time point. So I said, oh, I want, this is the time point in this data set. This will load in a second here. Come on. There we go. Okay, so this is an image, image of a toaster was sort of what the gripper was sort of interacting with here. And now I can run it, I can run a vector search sort of over that data. I can get the embedding back, and then here's where I search over the vector, get the best matches, and I will wrap up quickly here. I send all of that to the viewer again. Wait, because it's a demo. And there we go. So I've got a table here of like close matches to that, that input image using sort of vector search. I can't remember what feature embedding we used here, but I can then take these, and at each one of these, right, this is a time point in the source data, right? I can link back to this and end up right back at that original point in the data set, right? If I want to sort of see what was happening, how this worked in this particular episode. And so that is my whirlwind talk. I'm going to stop screen sharing this guy. Maybe no, my screen share is over here, a different computer. But yeah, I don't know if I've got time for questions, but if I,
yeah, let's give another round of applause. I think we can have one quick question.
Otherwise, we can talk at coffee. That's
fine too. Yes. So can you come up the microphone here? Yeah, so that everybody can hear.
Rob, thank you very much for the talk. It's very interesting. With Rerun, is it sort of agnostic to all of the other frameworks out there or systems out there? So could I, for instance, plug in whatever simulation or other tooling I want to it?
Yeah, exactly. I mean, that's very much, I think, one of our big focuses with Rerun from the very beginning was to make it as easy as possible to integrate into other frameworks and kind of be unopinionated about the robotic runtime, framework in particular, and then bridge into that. So we've built a ROS bridge. We've done integrations with other frameworks where you just log directly, right? You still have to use at some point, again, the data. Something somewhere needs to take that data and convert it right into this like canonical Apache Arrow semantically tagged information, but we've tried to make it as lightweight and easy as possible to do that.
Great, thank you very much.
Awesome.
All right, thank you.
Okay.
You want to go to the next
Perfect.
speaker? Yeah, thank you. Okay, so our next speaker is Dr. Angelo Cosaro. So Angelo is online today, I think. Angelo, can you hear us?
I can hear very well. Hello, everyone. Good morning, good
perfect.
afternoon, evening,
Right.
depending on where you're connecting
Yeah,
from.
so Angelo, before you talk, I just want to give everyone here a brief introduction about you. So Angelo is the founder, the co-founder of Zeta Scale Technology. So they developed this Zino protocol for distributed computing. And I think like some of us might use ROS2 here, and then you know that Rostro is actually using this DDS protocol, and then Zino has been very useful for like for the use case of multi-robots communications, and Angelo is also has been a well-known expert in a distributed computing area, and today he's going to give us a talk about what he has been working on in the recent years. Using Rust programming language for robotics. And without further ado, Angelo, the stage is yours.
Okay, thank you very much. So I will start by sharing my screen. And please just let me know if you when you will be able to see it. You should see the title slide.
Yes, we can see the slides perfectly.
Okay, perfect. So let's get started. So thank you for the intro. I had a quick slide on intro, but again, I think you covered it all. So, and just to give a little bit background on my education, I'm a telecommunication engineer by foundation, and then I did a PhD in distributed computing, which I think is very useful because those two community a very different view on the things that you need to do, the telecommunication people, versus the things that you can do, which is the computer science people. And I think it's good to have those perspectives. That has helped me a lot in designing protocols. I've been around and working on protocols forever because that's my passion. And again, indeed, I'm the guy that actually started and still lead the Zeno protocol. Okay, so setting the context. So robotics, if we want to make a parallel with ourselves, it's really about trying to make something that in a way, right, emulates the structural part of human or of living. Obviously, I mean, humanoid robots resemble more and more humans. But if you think any kind of automation, in a way, there is a structural component, and you can make a parallel with our body, right? Then the brain is the element that usually is used to somewhat decide what you're going to do with this body. And both robotics and AI are obviously very hot today as a topic. And what sometimes is a little bit surprising for me is that people when dealing with body, but also when dealing with technology, forget that these two things, the body and the mind, can only function as far as they have a nervous system that keeps them together, okay? And if we make, again, the parallel with our domain, nervous system is about making sure, right, the communication is working. Because otherwise, instead of being able to throw things and catch them like this, but we will be like clumsy Frankenstein. So we shouldn't neglect this because the more we want the body and the brain to be sophisticated, the more demand we have on the communication protocol. And today we'll be focusing on communication and Rust because I will be addressing, why Rust, what is our experience, and so on and so forth. So real quickly, the problem that we set to solve a few years ago, that was around 2015, was making sure that you could build a system that could span from a microcontroller up to the data center and leverage on a single protocol. Because before Zeno, there was no protocol that you could deploy on very small microcontroller that could run efficiently on constrained network that would cross the internet and still deliver very high performance in enterprise grade or data center like infrastructure. It is quite challenging. And again, but it's not impossible as we have shown. And when we started this project, most of the protocol that people were using even those that were considered quote unquote new, had been around at least for 20 years, if not more, okay? So that was the first goal, but it wasn't the only goal. The second goal that we wanted to solve was the ability of maintaining storage of data decentralized. Why is this important? Well, I had the chance to work in smart cities. I mean, I worked in Nice. Some of you might, if you've been in France, you have probably heard about Nice. It's not far from Cannes, and that's La Côte d'Azur. So I think it's famous in all the world. That was in 2008. In 2015, we did a bigger city, which is Barcelona. And then we were very involved in the Smart Nation project in Singapore. And the challenges that we were seeing, especially in Barcelona, where they have a very decentralized infrastructure, they have over 1,000 servers deployed over the city and connected by a gigabit network, was that we had the possibility to retain technically data on the periphery. But then it was very hard to keep track of where data was and understanding where you had to query the data, right, to retrieve certain set of information you were interested in. And so because of that, people were always ending up pushing all the data to the cloud with the consequences with respect to devices that, for instance, are battery powered. Okay, so those were the two problems we wanted to solve because, before, and again, these problems were problems that we could see in smart city, we could see in robotics, we could see in automotive, overall in IoT and edge, in aerospace, and so on and so forth. And again, back then, right, or before Zeno, when you wanted to build this system, it was really about stitching heterogeneous technology, building up what I've been calling the digital Frankensteins for a few years, crossing your finger and hoping that it would work, okay? So we started working on a new protocol. This new protocol is called Zeno. And by the way, for those of you, Zeno is both an acronym and a reference to two philosophers. But Zeno stands for Zero Network Overhead Protocol. And it's a reference to both Zeno the Stoic and Zeno, the pre-Socratic philosopher. Okay, Zeno is the first on its kind because it's the first protocol that managed to put together pub/sub and distributed query. And as such, it's technically a pub/sub query protocol. And we realized actually that the same primitive that we could use to issue distributed query to retrieve data that potentially was stored in distributed sources was the same primitive that we could use to represent a distributed computation. And as a consequence, we started, we aimed at solving two problems, but we solved three. So today, and this is, as we'll see, is heavily used also in ROS, with a single protocol, you can distribute data from the microcontroller up to the data center. You can store data, as we will see, on any kind of database, as far as we have a plugin for it, in a decentralized manner, and query data without being aware of its location from anywhere on the network. And with the same query mechanism, actually, you can have distributed computation and a very flexible way of triggering computation that can emulate things spanning from a very simple RPC up to a MapReduce. Okay, as we were targeting a performance system, Zeno had support since the very beginning for zero copy and shared memory. That's very important, especially in robotics system, but also in medical and in automotive, wherever you have high volume of large data like video, LiDAR, point clouds, and so on and so forth. Zeno, or the current version of Zeno, and I'll get back to this in fact, one slide, was written in Rust. Why Rust? As we will see, because of security, safety, and performance. First for us is security. Now, we write protocols, and a protocol runs on a network. And as you know, usually, right, if I try to hack something, unless I'm on site, I have to try to get in from the network or with an USB key, okay? But let's assume that you don't use the USB key trick and you're trying to get through the network. So the protocols that are used for communication are usually one of the point of attack or represent an attack surface for anything that is connected to a network and thus to the internet. And you should be aware that 70% of the security issues come from memory management problems. So the previous talk mentioned memory management issues with segfault. But another problem are, for instance, buffer underrun or overrun, okay? And those are used very often in C program as exploit, okay? I guess all of you know to exploit that. That's very well known, okay? So Rust, by construction, cuts 70% of those issues out of the equation, right? And it's a big improvement in terms of security. And then you can do some other, you have to do the proper protocol design to limit the denial service attack and all the other nasty things that might happen to a protocol. Performance. Rust obviously is a system programming language, right? And I mean, sometimes people, when they think at performance, they just think about raw performance. And if we make a comparison, right, Java, okay, in terms of peak performance or throughput, can achieve very good performance. But for the kind of things we do, it's problematic because of garbage collection, okay? And so here, when I say performance, you should really think as performance and determinism. And as we will see, the fact that Rust doesn't have a tracing garbage collector was a plus for us, okay? And then obviously safety. I don't know how many of you are involved in safety critical systems. We are. And we saw that the property of Rust would have been key for certification. By the way, for those of you, again, that are not involved in Rust, in safety, there is usually a list of languages that can be used for safe system that is maintained by NIST and IST. And before Rust, the only two languages that were in that list were C and Ada. And Rust was added, I believe, around 18 months ago. And by the way, we have now also a Rust certified compiler in the open source, and then it's very relevant for automotive, but also for robotics. Why? Anything that is flying in some country will have to be certified to some extent. And once again, Rust can play a big role there. Okay, getting back for a moment to Zeno. So again, as the previous talk was mentioning, actually, we build on Rust, but as you will see, we have language binding for almost anything you can imagine. And Rust makes that easier and easier, okay? I think when we started, the only way to go was cbindgen, but now you have framework for Python like Pyo3, which is just incredible, right? There are similar framework for C# and so on and so forth. Built-in support for shared memory and zero copy. And the other important aspect to consider is that when we designed Zeno, as you see in this stack diagram, we decided that the protocol was supposed to be run on top or able to run on top of a data link. What does that mean? Data link means is that we assume that the underlying network is able to transfer data from point A to point B, but not from point A to point B to point C. In other terms, Zeno does its own routing. As a consequence of this, right, Zeno can run on data link layers, including serial, raw Ethernet, Bluetooth, OpenThread, but likewise, we can run on higher level of the protocol stacks, like plain IP or TCP IP, UDP, QUIC, Unix socket, pipes, share memory, whatever. The other important thing is that in terms of wire overhead, if you configure Zeno for minimal wire overhead, you just have a handful of bytes that is added to your data. And again, this is very important when running on constrained networks. That can happen, for instance, if you are retrieving telemetry from devices that are deployed around the country. Usually company pay for the data plan, and you pay by byte. And that has a huge, actually, operational cost if you have lots of devices that transmit constantly, over an extended period of time. Okay, now, why Rust? And so you should know that actually, the very first version of Zeno wasn't written in Rust because we are just celebrating 10 years of Rust. And I mentioned that we started working on Zeno in 2015, which was just about when Rust 1.0 was coming out. And obviously for us, already back then, for us, Rust was quite appealing. Again, a system programming language, with zero cost abstraction. That was very important for us because, of course, we've done lots of C and C++, but in our company, we have a very strong functional programming background. So we tend to like programming languages that have those constructs and in general, we tend to like to write our software as much as possible in a declarative manner, okay? So that was very appealing. But back then, we discarded Rust because I don't know how many of you were trying to use Rust in 2015 for anything at scale. It was painful, guys, okay? And we said, okay, great, but not ready in early 2015. So we wrote the first version of Zeno in OCaml. How many of you know OCaml? Okay, maybe we can do a poll offline. It's an incredible language. It's a functional programming language that comes from the ML family. So just a quick intro, oversimplifying, there are two families of programming language, and those two families of programming language were somewhat shaped by two very influential functional programming language. One was Lisp, invented at MIT, right? And the other one was ML, the meta language, invented by University of Edinburgh. So Lisp, in a way, was a philosophy based on dynamically typed programming languages. So you write a program, you don't have any type annotation, and if you make mistakes, your program will fail at runtime. ML, which was a meta language introduced at the University of Edinburgh for supporting proof, had a very sophisticated type system with type inference already, by the way, in the 50s, okay? And so you can see already the two families of strongly typed and compile time typing versus dynamically typing that was created in the 50s, that division. But anyway, getting back to OCaml, OCaml is a very popular programming language in, the top engineering school here in France. And I think in Europe, it's still taught at Oxford and in US at Yale. Okay, so some of the top schools still teach this language because of, I think, its elegance, its performance, and additionally, the property that it has in terms of safety, security, productivity, and by the way, support for embedded systems. You can run OCaml on microcontrollers. So for us, it was perfect because, we were inventing a new protocol. We wanted a programming language that was, secure, safe. There are things like Coq and Gallina that you can use even to prove OCaml protocol. So in the first version of the protocol, we were using this tool to prove the correctness of some portion of our protocol. And again, we were very, very happy with this program. I mean, it's a very beautiful programming language while remaining sufficiently pragmatic. For those of you that are familiar with Haskell, okay, sometimes Haskell is a wonderful programming language, but sometimes it's too much for some people. And then if you use Haskell in anything at scale, you have to be careful with space leaks. In OCaml, you don't have this problem, and it runs very, very fast, okay? So why did we leave OCaml? That's the question. If we love it so much, right, why changing? Well, mainly, there were two reasons for which we had to make the camel sad, and I kind of still feel a little bit guilty, okay? So the reasons were, first, the lack or delayed support for multi-core. So adding support for multi-core in OCaml, was a very ambitious project, which was completed actually, I think 2 years ago now. And back then was, next year you will have multi-core support, but wasn't yet coming. The second problem was that we had some large industrial customer for Zeno, and they were very concerned about the limited availability of OCaml programmers because it's hard to find, and if you find them, they're also very, very expensive, okay? Because, they're used in some market where you usually need a few people, but very good. So, you have to be able to afford that. And so because of that, we decided, okay, we're going to rewrite Zeno. How are we going to rewrite it? And that was around 2017, okay? So, there were three options. C++, which kind of is the default option if you're doing system programming. And, I've done lots of C++. In previous life, I wrote actually an entire implementation of real-time Java in C++ that has flown in UAVs. So I know it very well. It's very powerful language. But again, we all know the pain that comes with C++. Then, some people or some customers were pushing from Go because Go is very popular for cloud native application, but I had a few issues with Go. First of all, for us, would have been moving from something that was very articulated with very high level of abstraction and a programming language that allowed us to really describe the types that make our problem space, define the invariants, be very compositional, moving to a language where you didn't even have generics, right? It's like, what the hell? And on top of that, we had to pay for a garbage collection, a tracing garbage collector. So we said, no way. Instead of pressure from some customers, said, forget about Go. And then our proposal was, you know what? Rust 2018 is about to come out. We're going to reevaluate Rust because we liked it a lot in 2015. We didn't feel it was ready. I would be curious to know, when you guys started doing Rust and when you felt that it was ready for industrial use. But yeah, so we reevaluated Rust, and essentially we decided to go for it before the 2018 edition was actually released. But we started working on obviously the nightly version of what was to be the 2018. And so once again, why did we decide to redo Xeno in Rust? Well, because of its memory and concurrency safety. That's very important because by construction eliminate 70% of security issues, because it delivers very high performance comparable to C and C++, in some case better. For us, it is very expressive. It has a super powerful microsystem, which is easy to abuse. And we have to put limitation inside because otherwise people start doing crazy macros. And that's there are some other issues with that. It comes with batteries because you have a great build and package management systems. And I think that the number of packages that exist and the level at which packages availability or crates grows, it's very good. It runs on microcontrollers. So that was an important thing for us. Eventually, right, we want to have a Xeno version written in Rust that runs on microcontroller. As you will see in the next slide, today, we're still using C for that, and I'll explain why in a moment, okay? And then obviously it has support for synchronous programming, which is a big plus for us. And it's a big plus for highly concurrent code like Xeno. So why this importance on asynchronous programming? Because whenever you do concurrent programming, if you don't have an asynchronous programming framework, usually you end up having lots of inversion of control. And inversion of control is very problematic because the semantic of your application ends up being scattered in a zillion listeners. So go figure out where is your bug. If you have asynchronous programming, all of a sudden you have the illusion that you are programming sequentially, although actually it isn't, right? But then it's much easier to reason about the semantic of your code and spotting logical bugs, okay? Okay, so as of today, we have two implementations of the Xeno protocol, okay? One of those written in Rust, and this is where all the infrastructure that we deploy and what Ross is using today and so on and so forth. And then for microcontroller, we still have a C implementation. It's exactly the same protocol, but written in C. Why so? Well, because as of today, the embedded ecosystem still is heavily based in C. We have done experiment. We have a subset of our protocol already in OSTD, but it's not the full-blown protocol. And we have more and more requests, so I'm pretty sure we'll get there. And that's also very appealing because if you think what Rust could deliver, especially with framework like Embassy on a microcontroller, it kind of resembles the services that you have with an embedded operating system. So you could run application bare metal just with Rust, potentially if you need, plus a framework a la Embassy, for those of you that are familiar with it. Now, because of Rust, obviously, we have support for anything where Rust runs, which is a lot of platforms. And then obviously for our embedded version, we support a zillion of platform because We have no external dependencies behind, a few primitives that we need from the US. The other interesting things for Zeno, and this is also very important for robotics, is that we have no topological constraint. Okay, so you can run Zeno peer-to-peer, and this is, for instance, the only topology supported by DDS. But also you can run Zeno in a mesh topology, and that's very important. If you have robot platooning, in some situation you have radio links. We have some of these applications in oceanographic robotics, and you have to be able to run on a mesh. What is the difficulty of running on a mesh? That application, so in this case, the peer of our protocol, need to route data on behalf of other application. But we can do even a little bit more, because sometimes you have some robots, like little tiny drones, that are so constrained that they cannot afford to route data on behalf of other robots. And so in this case, they can take the role of a client, peer up with the closest, let's say, robot that is running Zeno, and use that as an infrastructural node to route data between relevant parties. Then we have software routers. And again, a software routers is not at all heavyweight. Let me give you an example. So we'll be using this in a few minutes. So here I will have a router running. So a router is just some Rust code that runs very efficiently along with the entire Rust stack on a Raspberry Pi, because you have Raspberry Pis inside these robots, right? Let me put the robot back. So a router can be deployed essentially to build an infrastructure that spans the entire globe. By the way, I actually forgot to look at what time I started. How much more time do I have?
Think you have about 5 more minutes.
Okay, great. Yeah, so that's perfect. Okay, so something else that I want to make sure that it's understood. For how Zeno works, right, you have no topological limitation, but if you think the communication graph, each link of this graph can be of a different kind. So in this case, for instance, I could have an application that is communicating TCP/IP with another application, open thread with another application, serials with another, TLS with yet another. And it would be routing across all of those. I don't know any other protocol that can do this, but this is essentially in robotics. Because in robotics, sometimes I would talk with a microcontroller over serial, right? And you don't care because it's still Zeno for your application. You just configure a serial endpoint, okay? So this is just to summarize topology and put it in perspective, what Zeno supports versus MQTT and DDS. The other important aspect of Zeno is that we have a plugin system. And we have designed Zeno to be easy to integrate with other protocols or to support, let's say, natively integration, as well as with databases. And one of the reasons why Zeno started getting very popular in the ROS2 environment is that we had a drop-in functionality by which you could drop a router in your robot, enable a ROS or ROS2 plugin, and all of a sudden your robot, without any change, right, would start communicating robot. And especially if you had mobile robots, Zeno behaves much, much better than DDS in wireless networks, not to talk about wider networks. If we look at performance on server-grade hardware, this is a paper that was published now around maybe almost 18 months ago, maybe a little bit more, and our performance have improved since. Now we are about at 7 million messages per second for small payload. But in spite of that, this was run on some Ryzen 7 connected by a 100 gigabit network. And you see here the throughput that we deliver on a 100 gigabit network. It's worth knowing that the transport used here was TCP/IP, and that iPerf was saturating at 70 gigabit per second. Light blue is a publisher and subscriber for Zeno. Violet is a publisher, a router, and a subscriber for Zeno. This is DDS, a data writer, and a data reader. And here you have MQTT with a publisher, a broker, and a subscriber, and Kafka, similar topology. Whenever there was a mediating node, like a Zeno router or an MQTT broker, that was run on a separate machine, okay? So peer-to-peer to machine, if there was any mediation, there was a third machine, everything connected by 100 gigabit network. And if you look at the latency spans from 6 to 10 microseconds in this network, depending on whether you are sending expedite data in Zeno, which doesn't get essentially any scheduling, okay? Or if you're leveraging Xeno scheduling to maximize your throughput. Okay, let's talk a little bit more about robotics. So it was mentioned in the intro that Xenon has become very popular within the ROS community. And actually, that was because of some challenges that people were having with DDS when running on a wireless network. Well, DDS actually was designed for fixed networks, okay? I mean, I think this is something that was actually one of the design point. And I don't know how many of you know, but I was one of the guys that started DDS standardization in the early days. And I was the only guy that left it out of rage because there were some changes that I think we were supposed to do to the protocol that other vendors didn't want to do. Okay, anyway, and that's why I started Xeno. But the point is, the reason why DDS doesn't work properly on wireless network are two. Okay, one is that one assumption of the protocol is that you can leverage multicast and that you have essentially no losses or very little losses. And if you look at the system for which DDS was designed, which were closed system, like a ship, right, a combat management system, this is a technology coming from aerospace and defense, or anything where you have a well-dimensioned wired network system, in those systems, losses, packet losses, are exceptional, okay? They are not the norm. That is not the situation for a wireless network. And the other difference is that those systems are very resourceful. And DDS dynamic discovery, it's obviously very verbose, okay? Because there wasn't any real intent to optimize it because there were plenty of resources in those kind of systems, okay? Now, this is applying this to wireless scenario or trying to scale it to the internet actually doesn't work. And there are some other reasons. There are also reasons how the reliability works and so on and so forth. So, but this is not a presentation on DDS. I've done some webinar in which I explain what are the challenges. You can look on the Zetascale YouTube to retrieve those. Or you can look at this report from Open Robotics and Intrinsic, where they collect all the challenges of DDS users, collect the requirement for current and next generation robotics, and then they do an assessment of the various protocols that are on the market. And actually, the result was that Xeno came on top. As a consequence, it was decided to do a Xeno RMW, and the Xeno RMW will be tier 1 with Kilted Caillou that is coming out next, I think, Thursday or Friday, the 23rd. In the document, you will find this table, which is the mapping of requirement key for especially multi-robot system and mobile robotics and the different protocol, where you have CIFL, DDS, ECAL, Kafka, MQTT, NNG, and so on and so forth, even TCP, ROS, ZMQ. And Xeno comes on top. And then there was a poll that was made to the user, and even the user, the first protocol that ranked was Xenon, and the second one was TCP-ROS, which was the protocol that was used in ROS1, okay? So obviously the Xeno community is waiting for this, is very eager to get that. It will come next week. And in terms of the design, I will jump real quickly I just want to present the slide, and then we'll wrap up with some question. The RMW, by default, will have a router on each robot. Why so? Well, first of all, because in our experience, it's very important to decouple inside and outside communication. Why? Well, I'll give you a trivial example and a story from the trenches. I mean, usually, and this is an example with some race car, inside the robot, latency is low, reliability is high. As soon as you get out of the robot, right, usually network is not very good. And so suppose that you are sending images that need to be processed to nodes inside the robot. If you send the image at the same rate outside of the robot, that's actually not neither usually a good idea. So you want to do some downsampling. Where can you do the downsampling? Well, in the router, okay? That's something you can configure now with the ZRMW. I'll give you another example. In the DDS world, when using DDS with ROS, if I was a robot, everyone would discover everything I have to declare, right? Or all my topics. With a Zeno router, you will be able to configure what gets out and what not, okay? And there are you can decide how to deal with security, access control, and so on and so forth. Okay, and by the way, for those of you that were familiar with ROS core, the Zeno router is not necessary for having communication between the nodes because the communication is still peer-to-peer. Will enter into the picture when communicating outside the robot. And there are all the series of nice things that we'll be able to do to actually improve the communication in the robot. And more importantly, as the Zeno router is written in Rust, ensure that your robot, right, in spite of what the programming language you're using for your nodes, is shielded and all the communication with the rest of the world is happening on a stack that is written in Rust. And as I mentioned before, that's a good advantage for security. So in summary, and then I just want to quickly show you something. So Zeno, in a way, it's a kind of a protocol. It unifies data in motion that address and computation from the microcontroller up to the data center. And again, modern robotics applications have that span. And as of today, is considered as the best protocol for robotics. And of course, is written in Rust for security, performance, and joy. Because even in terms of productivity, I think in the beginning, we weren't as close as the productivity with OCaml. Maybe we are still a bit below OCaml productivity. But in terms of comparing with C++, our measure, and again, you know that we developed the protocol for the microcontrollers in C, we have at least 2x productivity when writing Rust code when compared to writing C++ code with programmer at the same level of skills. And last things I want to show, the robot that I was showing you before, I need to see I see my image. So what I'm gonna do, I'm gonna unplug this. So you can see oops, what happened?
Angelo, I think we just viewing your desktop.
Yeah, for some reason my video stopped. Can you see my video now?
Yes, we can see your video.
And yeah, can you see now my browser?
Yes.
Okay, so we are going to teleoperate this. And let me turn it around. Can you see the robot move and the browser change? Yeah, this is being teleoperated across the internet using Zeno. And any of you, I'll put this in the chat of the meeting, you will be able to teleoperate. So don't hesitate to try to teleoperate. Okay, and that's just a Zen infrastructure with once the Zen, yeah, someone is playing with it. Yeah, and you see how reactive it is? Yeah. And by the way, here you're teleoperating because Zen also has REST API. So this is using Zen REST API through an infrastructure that we have deployed. Let me show you here. So this is the robot. And let me show you something else real quick. And if I have a plain Zen application, I want to subscribe to the bot scan. Here I'm getting the scan. Okay. Okay. Yeah, and you see that my application has been discovered. And if I stop the application, it will be undiscovered. So you will be able to play with these things once you get the ZenRMW. And there is already ZenRMW, but you have to build it. Okay, so thank you for your attention. Again, it was a pleasure for me to have a chance to give a talk at ICRA. I hope that you guys enjoyed this talk. And if there are any questions, I'm here to answer them.
Thank you so much. So I think we are a bit over time. I think just one very quick questions.
Sure.
Anyone? Yeah. Okay, so we don't have anyone like have quick questions, but like please folks use Zyno, okay? Try Zyno in your robotic system and you will see how amazing they are. But thank you again, Angelo, and it's amazing talk, and we will go to the next talk, okay?
Okay. And by the way,
see you around. Right.
We forgot to mention that it's entirely open source, so I'll put the link, right? Because I always forget to say that. I give it for granted. Yeah, here we go.
Of course.
Okay.
Yeah.
Thank you, guys.
Thank you.
Take care.
Thank you. All right. Thank you so much.
I'll stop sharing my screen. Yeah.
All right. Let's go to the next speaker. We have Guillaume Binet from Copper Robotics. So Guillaume has been like having like 25 years of industrial tech experiences. He has spent the last 10 years focusing on robotics specifically. And he has been involved in multiple different like industrial roles, like CTOs at Skyways drone company, VP at the core platform Motional, which is autonomous driving company, as some of us might know. And also he has been also a VP of the onboard infrastructures at Argo AI, which is another autonomous driving company. Okay, so Guillaume is going to give us a talk like to try to convince us why Rust is a game changer for robotics. So now I think like Guillaume, are you ready?
Yes.
All right.
Sharing my screen.
Okay. Maybe you just directly use the laptop here. Yeah, go into the Google Slides.
Can you the presentation?
Yeah, just put it on the chat maybe if you don't mind. Yeah. Discord here.
Or which
This is the conference laptop. Yeah,
chat
of the Zoom chat.
of the Zoom, okay. The chat. Okay. Well, no demo for today, but right.
All right. I think we also need to share the screen on the Zoom.
Here we go. Thank you so much for the setup.
Problem. Nice. Here. Yeah. All right. There we go.
Good. All right. Thank you so much. So, yeah, so I'll switch a little bit gears because I did this Rust presentation at a previous conference, and I would like to focus a little bit more onto Copper, but there are a lot of like intersections about like why I actually build Copper in Rust, and why actually I encourage the community to use Rust to actually build upon such a framework. So a little bit about myself. You can go on my LinkedIn account if you want more details, but I got presented. So what is Copper, right? Copper is like an SDK and runtime for robotics. So we have one of the OG of the robotics operating system here, right? But I'd like to actually like kind of name it also a kind of an engine for robotics, and you'll understand a little bit later for why. So what we will go through is first like why another robotics framework that often like the question like a lot of roboticians ask me like why do you do something new, right? Oh. Thank you. I'm a Zoom incompetent. And so then, like, why Copper is kind of on its own category, right? Like, it's not like a lot of like Rust project. You see a lot of rewrite, right? You see, oh, somebody did I don't know sudo -rs and rebuild it. No, Copper is completely different, and it's really comes from the experience I had in robotics, right? Then how we leverage Rust, that's going to be the part for why Rust is amazing. And then I'll try to show you, so I cannot demo you, but I'll show you a little bit like some code and how it interacts and how you interact with the system. So existing solutions. So what I've seen, right? Like myself, I am a software engineer, right? Like more like a bits and byte guy, like doing like really deep into computer architecture and making code fast and so on. And so I did like 3 autonomous companies, like we were saying, right? And in none of them we use ROS. And one of them we started like it was like 10 people around the table, and Brett Browning, you probably know the guy if you're in robotics for a while. The first thing he told me, you do not use ROS. I was a software engineer, I was shocked, right? Like, what do you mean? It's there. The ecosystem is huge. Like you have a lot of support, we can leverage a lot of things. No, what we did, like 3 times in 3 different companies, basically rewriting a framework. And I started to understand why, because we made the same mistake as ROS, like for a couple of them, right? And some like nature might shock you, right? For example, one thing that doesn't work really well is asynchronicity in robotics, and we'll see why, right? And the other one is the non-deterministic aspect of that asynchronicity. Basically, anything can happen anywhere, anytime on your robot. Good luck actually rebuilding the entire context to be able to reproduce that on your laptop. And yeah, and at the beginning it was probably not an issue, but like robots are getting like more and more complex. You have like a bunch of like sensors all around the robot, like a lot of like algorithms working on it. And yeah, being able to restore those contexts are really important for you guys, roboticians, to actually develop your system, but also for safety. We'll see that also, right? C++ also started to be a problem. Like I spent nights on self-driving cars, wondering with a developer telling me, oh yeah, you know what, the CUDA driver is the issue in the system. No, it was an undefined behavior in the C++ code base that was actually trashing the communication with the driver with CUDA, and the GPU itself was crashing on the other side. So good luck finding that. Like that was really painful, right? Also ROS in general, like the performance is not that good. And also a lot of like returns of like people are really struggling putting that in production for kind of the sum of all those issues we have on the top, right? So okay, from that kind of background, right? What I try to get my inspiration from is more like the gaming industry, right? In the gaming industry, you have things that were, I don't know if you are old enough to know those games, but I think that's like in the 90s and like early 90s, mid 90s, and then 2000s for 2017s for the right-hand side. And that to show you a little bit like the evolution of the professionalism in the gaming industry. At the beginning, like on the Prince of Persia, for example, that was literally a dude in his garage, flashing with a stroboscope, like his son, to actually pixel by pixel drawing those animations. Everything that was uncoded, everything was in assembly, and it felt like what I lived through with my like at the beginning of the autonomous vehicle industry, right? Then we had kind of we really had a pivotal moment, right? Like with Doom and so on, where people started to actually build engines to build games and not trying to build games directly, right? And those engines at the beginning, they were very specific, like this one, but now you have Unreal and so on that are that are really like versatile. You can actually have a lot of like various people that can work on it, that are not software engineers, like the beginning of the games, right? You have like, I don't know, people that are making 3D assets or like making sound effects or like, I don't know, like color grading, all those kind of like professionals that are not directly like programmers, but that are all interacting, guess what? In a real time, like time critical environment like a game. So that was basically the starting point of Copper, right? Like, how can I make like a framework that is not really focused on just making a demo and putting things together, but really having something like a real engine where you have hundreds of millions of dollars actually built on those engines. So that's basically almost like the flip on the previous the couple slides before. So Copper from the get-go had to be deterministic, right? Like at Argo AI, I had to do it like 3.5 years in. And it was painful, right? It cost a lot of performance. You can imagine like in the big asynchronous systems, you need to actually start to get all the events and be sure that which one was actually happening at one point in the timeline, right? It's designed for safety. That's also something like with those new robots are only useful if they are close to you, when you think about it, right? The all industrial robots in their cage where you are, or lasers if you approach them, they stop, right? For me, that's more like kind of like, that will always exist. It's very, it makes money. It's easy to do. But that's not where the world is going, right? They are going to humanoids that's going to be close to you, or cars, or like little things on the sidewalk and so on. So safety also had to be from the get-go in the core design of Copper. And performance, right? Performance. The thing is like often people come back to me. So why do you care? But performance is, well, for one, safety, right? Like the more you can actually squeeze from your system, the more you can observe the world, the more you can actually react to it. And also, it helps developers to actually abstract better their systems, right? Even if you think about like let's say like an ML-driven like robot, right? You will always have components. And the more components you have, the more actually overhead you will add to your robot, right? And what I've seen in companies, right, like LMs, but like a bunch of companies, they start to say, oh yeah, we decompose well our robot, we have a lot of components, and they are like, oops, we need to put that in production. And they start to bundle components 2 by 2 and 2 by 2, and they end up with like almost like a big one ROS node on their robot, which is absurd, right? It beats I mean, it fights the purpose, right? Of course, like in terms of philosophy, like we were saying for the game engines, I want developers to actually focus on their algorithms, not bits and bytes and buffers and timings and all the things they don't care about, right? And then one pain point on the robots you see, and you know that if you build robots, right? The tuning is absolutely horrible, right? Like especially when you are getting like close to the machine limits, you are like, okay, it's okay, we will release it. You and the robot, you spent like days out tweaking like some priorities and so on. You make it fit, and then like, oh, by the way, we forgot one component, and here again, oh, you are adding threads, removing threads, changing nice nice on processes and so on, right? So okay, maybe I can do that. Sorry. No. Okay. So here, what I was showing. So basically, in an asynchronous system, right? You have components. You can imagine. Okay, you have motion planning. If you have a classic robotic stack, control and so on, right? And you have messages coming at any moments from anywhere, from sensors down to actuation, right? So it's like an asynchronous flow where you have events that are coming randomly on the system. With Copper, what we do is instead of letting the system schedule like that, those asynchronous events like it wants to do, we basically pre-compute the scheduler, and then the scheduler, we put that on the robot and we follow that scheduler synchronously. So it has like several advantages. So the first one is that you are always linear on all executions, on all the loops of your robot. Remember the games? This is what games are doing. They do have what we call a game loop, and they are doing always the same thing, and they can push billions of vertices per second, like easy peasy, like they are eating that for breakfast, right? Roboticians, they tell me usually, oh, we will have a point cloud of 100,000 points. Like, what do you mean? Like you have like gigahertz machines that are supposed actually to be able to push that through, right? And games are doing that by doing everything like linearly in memory, and that's what we do. Basically, Copper is building for you your game loop for your robot. It's a little bit more complex than a game because it depends on how you build your graph, right? Your graph of tasks. So it will and how it's actually scheduled. So it will build that. We were talking about like macro abuse on Rust before. Yes, we have been abusing macro a lot to do this. Basically, conceptually, Copper is a compiler. You give it a graph, it compiles basically this scheduler, right, with like what we call an execution plan, and and how you can tune it. Basically, you deploy it, you test it on your robot, you collect data, and from there you can actually optimize the execution plan. And so, okay, cool. You say you're performant. We are really performant. Like we have 100 times. We are 100 times less latent than ROS2 out of the box. We have like a little example in the repo in Copper where I basically have the same like minimum tasks that is actually just flipping a Boolean, right, through 8 layers, right. From like the green one is basically sensing, and the blue ones are actuation. It actually runs. You can run it on a Raspberry Pi for real, right, with GPIOs, but you can run it in simulation, right? And yeah, because we are all linear in memory. There is no wait. There is no lock. There is nothing the thing waits for, right, along the way. So task to task, we are basically at the speed of the processor, which is basically in nanoseconds. So think about it, right? For a developer, it means that if they want to decompose their system, it is free, like literally free for them, right? So if they are, instead of having like one big component, input, output, suddenly they can gain introspection into what is happening between 2 parts of their component, and they can do that and subdivide that as much as they can, because like it's almost free. Yeah, the data logging was really fun too, right? Like the first time I tried, I thought I made a mistake, right? To be honest, right? Like so same story with Copper. When we log, we have one execution loop that is linear in memory, and when we serialize that to disk, we get it and we put it on disk, right? We serialize that on disk. We don't even need a file system. Give me a block device, and you're good to go, right? And it means that yeah, it's like everything that your computer is actually made for, right? It pre-cache all the pages, it eats the cache all the time, and so on and so on, right? So Ross was using like SQLite. I'm not sure who had this idea in ROS2 to use SQLite, but I'm sorry, this is absurd, right? So you see the mentality, right? SQLite, your robot is doing a lot for you. Why? Why the robot is working for you? No, it should not index log transactions and so on and so on. It's pointless, right? The only thing your logger needs to do is logging data, and you are using basically your disk. You're trashing completely your disk, just doing like random commits on the disk, right? But still, right, even MCAP, we are 12 times faster. MCAP is pretty linear as an encapsulation, but still, right, like because we are just using memory map file and going like as fast as we can on the disk, we are still like an order of magnitude faster than MCAP. And other things, one thing that's something I learned along the way, when you debug your robot, usually you put debug logs, right? You put like some prints in the middle of your code, right? And it kind of sucks because you have this like very rich structured data between your tasks, right? And you have this completely unstructured thing that you need to do because you need to see if this data is there or not, right? Copper is basically compiling your debug statements and makes that as like a structured data on the other side. So for example, if you have this debug line, the string does not appear in the executable. It's basically an index, right? That you will have a log reader that contains like string number 152. And those key values on the right-hand side is going to be actually like a kind of a big table of those debug statements. So suddenly you can query in it, you can trace them, you can have a graph of them, and it's when you don't compile them, it's free. It's just remove them from the code base. So again, like those little things are coming from I was in a self-driving car trying to debug my thing, and oh my god, again I need to make a graph about this thing, and you do grep set thing on your gigabytes of text data. Not fun, right? And the other like thing, because we are talking about the Rust, right? You have this emergent Rust ecosystem. You've seen Fire, like that starts to be really competitive in terms of like algebraic computations, right? Linear algebra, and you have NAlgebra, which is like kind of the ancestor of that, right? Cornia in computer CV, Bevy, which is like a game engine, right? But it can be used for like few people use that for simulation, and we do have few demos with Copper with Bevy as a simulator. Avian is like a physics engine that can be plugged into Bevy, so pretty cool for your simulation. ICRA2025, we saw Zeno rerun, right? So all those are actually now native with Copper. You can use them. You can send like for example, matrices. You can convert them from those linear algebra. We use Cornia as a node. We did the Zeno communication, and actually the Zeno ROS Copper to ROS bridge is actually coming up. The PR is up now, so people can migrate from slowly from Copper to from ROS to Copper. And rerun is absolutely amazing. I mean, guys, I'm not sure, it's one of the best API ever used. It's so easy. It works so well with Copper. You just dump your line and pop, you have your data popping up. In terms of so that's more in terms also into the Rust ecosystem, like kind of integration. It's a delight, right? We have like for example, if you want to start a project, we integrate with Cargo, so you can build with a template your project. Building is just Cargo build. You have nothing to install. I mean, I posted on LinkedIn like a small demo on your Android, and like in 3 lines of command lines, you run Copper, right? Like with Rust, good luck with doing this. This is really daunting, right? Like compiling Rust. All the unit tests are very easily accessible, and we saw that before. So cross compiling also is just done, right? And another really interesting point of Copper, it's one executable, right? You don't depend, if you compile that, for example, with Muscle, it's not Muscle, but Muscle, which is like a glibc that you can actually statically compile into your executable. Suddenly, that's it. You have your executable, you put that on your Raspberry Pi or your NVIDIA platform, and here you go. This is the only thing you have to deploy. I wanted to show you like a demo, but I cannot. But In concept, it's very easy, right? Like those are the same concepts that Ross is building on. You have a directed acyclic graph with tasks where we define some IDs. Those are types, straight types from your code, from your Rust base, like a tree in your cargo.toml. You have some configs and you make connections between your task at the bottom, giving them the type of what you want to pass between the two, right? Those tasks are like in the same process, you can imagine, but you can actually choose to distribute your system, right? Instead of having that by default, like Ross, I prefer the developer to actually think about their system where, okay, if you want 2 coppers, yeah, sure, one primary, one secondary, and then you will have like tasks that will communicate from one to the other through Zeno, for example. It's supported now. Implementing a task are just a question of like callbacks. It's not like very interesting, but you can see there is 0 copy. So basically the framework pass to the developer a clock. So that's also like something. Every time you have a robot, the clock is really important. So that is actually built in Copper. It can actually be overridden and so on. And when you have like, for example, a source, I give you like a mutable reference on the bottom right, for people that read Rust, mutable reference of the destination message where you can write to. So today, Copper runs on a self-driving truck. So we have a customer in France called Convoy, and they are doing this migration. They were a Rust shop, and they realized that they were hitting a wall with their self-driving trucks. So they are rewriting from the top, so from the sensor down, layer by layer, and they have contributed actually the bridge between Copper and Rust. But also on drones. So I flew that at home. Again, that's wide drones because it really shines for Copper. It's very small, embedded. You need to be really fast, right? The latency needs to be low, and it worked like pretty well, right? Like the interfacing with the flight controller was pretty easy. And hopefully, maybe one day we'll compile with Copper with no STD, so basically straight to the embedded platform, and basically implement like an actual flight controller out of it. And so time for questions. Sorry I could not do like a quick demo, but you have on the GitHub like a couple line of bash that can make you actually try with a little simulator, actually Copper with a simple like a balance bot if you want to play with it a little bit. How are we on time?
Yeah.
Cool. So any
questions?
Any questions?
Yes.
Go ahead.
Come on.
Thank you very much for the talk. My name is Christoph. I'd like to know, I don't know, I'm starting with the hard question. How does it compare to Dora RS?
Can we wait for we are both on the panel, right?
Right after.
Yeah, so we'll have a little comparison about it, right? So what a little bit I can say, you tell me if I'm wrong, right? Like really Copper from the get-go come from the industry, right? Comes from the struggle I had with like self-driving cars and like real like collaborative robots, like very low real-time type of things, and the struggle to actually put that in and having like a Lyft and Uber and so on as my customers, right? And I believe that makes like a kind of Copper less good for like experimentation or education, for example, right? You like that's where Ross actually really shines, right? Like I've been bringing on Ross for like half an hour, but actually it's really good, right? And I believe Dora also is really good for this, right? Like having like for example Python bindings are amazing to actually you're on your robot, you want to test something and you go into it, right? We don't have Python binding for actually the robot runtime. We have that to export data, but I don't want Python bindings in Copper, right? I will, if you make me like a PR, I will block that PR, right? Because you don't want that in a self-driving car for safety, and so on, right? And you know that, like when you developer starts to, oh yeah, Python is actually really easy, and suddenly, yeah, you're blocked on your project, right? So yeah, I think the where we are coming from our frameworks are a little bit different. There were other questions.
You mentioned that the job graph is acyclic. And this is something like I built similar frameworks inside of Magically, but very similar, inspiration. And one of the first things that we hit was then like someone would go, but I have a recurrent system, right? I need to feed some state back into the system. And I'm curious, like, how do you handle that in Copper?
Yeah, so you would need to go externally, basically, right? You would publish that to actually subscribe to, like you would have a sensor on the other side, right? And then you still conserve the actual determinism, because you consider Copper itself as an external system that you record your own, right? But yeah.
Right. So I think we're actually a bit 15 minutes late, but we will have no, it's just in general the schedule, but like we will have a 15 minutes coffee break from now, and then we'll resume 15 minutes. Right,
Thank you so much.
Thank you.
Oh, you have some Copper goodies at the back if you want, like some stickers and so on.
Yes. This help. Yes. You wanna use the laptop to present or use your own laptop?
Yeah, I want to see whether test out.
I think we can try, because we're not using the sound. I mean, I'm not using the sound. Maybe we can just use the HDMI to project.
Yeah.
We can have a try. Yeah.
Yeah, you want to keep it short?
Yeah. Do you have an HDMI like input or? Right.
I have. HDMI.
Yeah. Okay.
That's good.
Try it out. On the thing? Yeah, maybe it's better. All right, yeah, I'm gonna right.
Yeah, that looks good.
Looks good. Yeah, it's kind of like the cable is kind of not great. I think it's okay. I think we have it just in.
All right, perfect. Thank you so much.
Anyway. Right, let's try to get this out. Try to get this up. Right. Right. Is this okay? Thanks. I think it's okay. Okay, it's a bit. Yeah, I'm gonna try the HDMI as well. There you go. And then. Do you think I have more cable? No, all right, that's fine. All right, there you go. Then I'm gonna bring this up. Thank you so much. It's working, and then maybe I'm just going to like screen share.
Went out to
Those just
We don't know each other, but like no Claire. She's at the board of.
I'm gonna stop sharing.
Oh, okay.
Is it your screen or?
I think it is on your screen, Tara. It's your screen. Yes,
No.
it is. It is your screen. It's a mirroring of your screen. No?
I don't think so.
Yeah. I think it's your screen.
When I try to plug in the plug.
Is it because the mirroring or?
But not really, because it's not the same, because I don't have like.
Schedule the website. I think it's on the website. No?
It just says speaker 1, speaker 2, speaker 3.
I can take a look.
Be nice to know the
And then you. Yes. Fantastic. Perfect. Oh, yeah, yeah. More of this where it's connected. There.
muted. Can you hear me now? 1, 2, 3, 1, 2, 3. Okay. Perfect.
So I think we can start now. So our next speaker is Haishen Tao. We can also call him Javier. So Haishen is Javier is a founder of 1 millisecond .ai, and he's a French software engineer. He developed like practical solutions for ML and AI users, engineers across like through open source projects. So now Javier is currently fully invested in Dora RS, robotic framework project. And Dora RS aims to make building robots fast and easy. So I think also today he's going to show us how he's going to leverage Rust and Dora RS to build AI robotics. Okay, right. So the floor is yours.
All right, thank you very much. Yeah, so today I'm going to talk about, I think there's an echo maybe, or yeah. Maybe it's from this computer, or something. Just give me 1 sec.
Are you on
Yeah.
Zoom here?
Yeah, yeah. All right. I think if I cut this, all right, this is a lot better. Everyone can hear me?
Sure.
All right, great. I'm just going to double check if I'm here. Okay. So I'm going to talk about Dora RS. I'm going to try to answer the question about like what's the difference between Copa and yeah, kind of like I think many people haven't tried Dora yet or have looked but never really like used it. So I think this talk is really about like how to get started with Dora. So a little bit about me, I'm Haishen Xavier Tao. I work full-time on Dora for the last 3 years, even before ChatGPT, when coding was pretty hard. And now it really developed. We used by Hugging Face. We more and more used by other companies, and especially companies that develop AI models that want to implement them in robotics field. I'm going to be doing a talk with Meta next Thursday in Paris. But anyway, so what's Dora? Dora essentially is something that helps you connect robot, camera, sensors with AI models, right? This is kind of the big premise that we want to do. The rest we care, but a little bit less, because this is already like a pretty big deal. And if we can do this, the rest is kind of like less important. We're trying to build on all platforms, Linux, Mac, Windows, because we know that everyone from all those platforms want to do robotics. We're trying to do Python, work with C, C++, and Rust. And I think this is one of the big difference between Dora and Copa. If you use Python with Rust, you will see that there's a lot of limitation. The first one being the GIL, and the GIL being this thing that doesn't let you do like a lot of parallel processing, right? A lot of threading doesn't work with the GIL, and it's kind of like necessary for Python to work. At least for now, maybe in the future it's not going to be, but for now it is. And so that's why in Dora, most of the things are in different process. So we spawn multiple processes, multiple Python instance, for example, and this is how we try to make everything work. The reason that we do multiple process will make Dora less efficient than if you just have one big Rust project, a Rust process, and then you can compile everything and optimize everything. But this is a trade-off we're more than happy to make, because then we can integrate a lot of the Python ecosystem, right? And beyond this, one of the big things we're trying to do is make accelerators work really well for robotics, right? So let's say you want to use NVIDIA CUDA. We really want to support this very, very well, so that you can have multiple processes that can share CUDA buffers together and do them in parallel, right? Because we believe that this is going to be a very big thing in the future of robotics. And hopefully we can make this agnostic, so we can make an abstraction so that this works both with NVIDIA CUDA, but also with Apple Metal and any other type of hardware accelerators like Huawei Ascend, for example. And the one last big thing I want to mention is that it's a big problem about doing something like ROS 2 or Copa is how do you distribute the software, right? So let's say you have a community that all wrote their own software. How do you make sure that everyone can like get it on their own computer and it just works? We do this using PyPy and crits.io mainly. And the reason that we do this is that it enables us to ship software that is pre-compiled so that you don't have to compile it yourself, right? And so a lot of the packages that you want to get from the ecosystem will be pre-compiled, even though it's written in Rust, even though it's written in C and C++. And this like makes it a lot easier for the people to get started and use it, right? So for example, I will show you a demo with rerun that will all written in Rust, but yet you can still pip install it in from Python and just use it. And so you don't have to have cargo install, you don't have to figure out which machine you're using. It works on both any architecture, x86, ARM, and any type of OS, okay? All right, so this is kind of a big overview. Maybe you want something more concrete. So the big idea of Drawer is kind of to start from a YAML where you define all your robotic application, what you want to use, your sensors, for example, a camera, the model, the AI model you want to use, and all the type of things like visualization. So I mentioned rerun. And then the thing is that you want to connect them, right? In robotics, you probably want to have the camera sending an image to an AI model, and then you want to visualize everything with a visualizer, such as rerun, for example. And so how do you make this work? The first step is to install all the software together. For this, we have a build argument in which on every node, and then we're just going to say, oh, I want to pip install this dependency, right? And so when you install this dependency, it's going to be added to your PaaS system. If you use a virtual environment, it's going to be added to your virtual environment. If you're using UV, we're going to directly use UV to put it in the right place so that you have a big isolation between your different robotic projects. Otherwise, it's going to be a huge mess. And then when you're going to run it, we're just going to call the path, right, as you would do on any command line. And so we're just going to find for the best match of the OpenCV video capture, for example, path, and then we're just going to run it as a process, right? And then you probably want to connect those processes together, and so we have a system called output and input, and then you just say, okay, so I'm going to output images, and then you will have nodes that say, okay, I want to listen to this image, right, from this node, knowing that you can have multiple subscribers and you can have as many like output as you want and connect them together. And we're working on making this as well distributed. I'm going to try to make a demo, but it's not yet stable, right? So be aware. Okay, so for example, this we have a camera. It's going to push images, so it's going to be like the input of the VLM and the plot. Okay, and then for example, another example that we have text, and then we have a plot. For now, we have a very simple definition of what an image is and what a text is, but hopefully we can have a specification at some point where every node will stand with the same specification, that everything is abstracted, and then you can like use it in any way you want. You can also use environment variables in the same way as you would do in Docker or in Kubernetes, and so you can you can have more configuration of your different nodes, right? In this case, I want to specify the height of my image. It could be the width. It could be other things. All right. So maybe even more concretely, yeah, what's going to happen is that when I'm going to say Drawer build, Drawer is going to spawn multiple pip install processes that's just going to install it, right? There's nothing more crazy than this. It's just pip installation on your node environment. And this is probably like something similar to what you would do in Catkin build, Colcon build, but the very big difference is that everything is precompiled, so it's just going to take matters of seconds to be installed. The second instance is how do you run the process, and what we do, as mentioned before, is that we're just going to call the process OpenCV video capture, for example, or Drawer Conveyor, and then it's just going to run as a NIMDevo process, and then we're going to use shared memory to communicate between them, right? The thing is, we work really hard on performance because I think it's important, and being able to do shared memory really like makes a big difference between TCP/IP or any type of other communication platform. And the big thing that we try to do is do shared memory with zero copy. And one of the big difficulty of doing this is that you have to make sure that when people read the data, it still exists and there's no problem. And we assure this by referencing counting across languages to make sure that every reference is still available and you never like read into random access memory, right? All right, so maybe I can do a quick demo because I think we talked a lot today. Maybe you want to have a feel for it, and I totally understand. So for example, I have a quick code right here where I have a SO100, which is this robotic arm. Okay, I have the camera, which is right there. Okay, and then I have a plot that I'm going to show later. I've already built it, and for the sake of making this demo work, I'm not going to rebuild it because I'm afraid of. All right, you know what? I'm going to build it anyway. That's right. So if I want to build it, I just say draw build, the data flow, YAML graph, and then I specify UV because if you never heard about UV, it's a package manager for Python, which is really powerful, and now it's kind of a feature flag. In the future, we hope to make it stable, but for now, it's basically gonna call all those pip install that you'll see right there, and it's gonna be pip installing. Knowing that, for example, for rerun, pip install is able to use cargo to compile the raw rerun, which is a Rust compiler, and then do the linking and then put it in my UV environment, right? So it doesn't mean that it's pip install, that it's just Python script, right? All right, so then when everything is installed, I can just do draw, run, no talk, and normally it should run, and there you go, it's running. So, yes, sorry. So hopefully it's running, okay. And so all node is ready, all right, so I can see, and this is my visualization using rerun that we talked this morning. If you were not here this morning, Jeremy made a really good talk about it, and you can figure out everything about it. And so, for example, in this case, so I have a 3D camera, a depth camera, that do RGB and depth, that is running real time. So if I put my hand, you should be able to see my hand. And we also have the robot that I mentioned before, which is the SO100. And if I move it, the camera is going to move it at the same time, which is because I have a 3D representation of my robotic arm, which is right there. And hopefully the 3D point should match. So they don't match perfectly because this setup is probably not perfect, but you can probably make it match very, very well. And the idea is that everything run in real time, right? And this would work with multiple robots, multiple cameras, multiple different type of robots, just from the YAML configuration, right? This is kind of the idea. All right, so that's cool, and okay, so I'm gonna stop it. All right, there you go. But we talked about, this is cool, but we talked about AI models, and you probably heard about AI models before. And so let's do a model, let's do like an example with an AI model. Right, so I'm just gonna use my QuantVL model. So what I'm gonna try to do, and I'm not sure it's gonna work, but hopefully it should, is it's called multiple models together, right? So as you've seen before, you can call one model, but you can also call multiple ones. And by chaining multiple AI models, I'm gonna try to make the robot make a hot dog, right? So for example, in this instance, what I'm gonna do is talk to the microphone. So I have a microphone, Dora microphone node, and the microphone is gonna create an audio. So it's gonna be going through a voice activity detection, which is just gonna basically say, oh, is someone speaking or not speaking? And then I have another model called Whisper, which is gonna be able to transform the speech to text, okay? So from the audio to text. And then I'm gonna have a VLM that is gonna be basically able to understand what I'm saying. And all right, there you go. So I have a pass whisper that's just gonna do like some wrangling, but basically the whisper is gonna be understood by a VLM. And at the same time, the VLM will also have the image stream from the image camera in RGB. And then he's gonna give me a bounding box. And the idea of the bounding box is that it's kind of a localization of the object I want to do, right? So for example, in this case, I want to grab or release an object, or put an object, and so he's gonna give me the bounding box of the object I want to take, right? Now the thing is, if you used VLM before, they're really good, but they're not really precise, right? And so in this case, we're gonna use SAM2, which is another AI model developed by Meta, and it's gonna be able to take this bounding box and then look at the image and then give me a very accurate segmentation of the object. And then basically I will be able to pick it up and then do something with it, right?
So if I want to run it, I just have to say Dora run this YAML that I just shown you, and there you go. And then I'm just gonna say run, and then it's gonna spawn all the nodes. It's gonna load all the models, and they're gonna all be connected together through the YAML configuration, the input, the output. And so now it's loading the models, and then okay, and now it's ready, all right? So now we can see the model in 3D. Right, and so now I activated the torque, so now the robot arm is gonna be able to move. And if I want to make it something with it, so I'm just gonna double check on something. All right, so if I say, grab the sausage, he's gonna be able to grab the sausage, right? And this is, all right, chill out. Can you put it in the white plate, please? All right, so you can add the white plate, there you go. So how did this happen, right? This happened because so for example, for rerun, I'm just gonna go back in time. Hopefully it lets me do it. All right, there you go. So when I say grab the sausage, basically I get the bounding box, and then, so he gets the bounding box, and then from the bounding box, basically I can have a segmentation, which is not very easy to see. Okay. And then he's able to pick it up, right? I might just finish the demo, and then I can show you later. Put it in the bread, please. All right, there you go. So basically, the VLM is doing the localization, and then I do a lot of image processing that makes me able to pick it up. And this is kind of the power of like combining multiple model is what I'm trying to showcase here. There's probably people who do way more cooler demos in this conference, so I don't want to, you know. But yeah, and then the idea is that you can also chain it to do something more complicated, like a hot dog. So if I say, make a hot dog, basically he's gonna, all right, there you go, it's fine. He's gonna try to chain all those comments together. All right, I'm just gonna try again, maybe. And then, all right, I'm just gonna try again because he kind of like messed up real bad. Can you make a hot dog, please? All right, there you go. So then, let's say this is cooking, so this is cooking, all right. All right, so it didn't really work properly, and we're not there yet, all right? I just want to make clear that it's still an ongoing progress. There's a lot of things I want to keep on adding, but the idea is there, right? So if you add multiple models, it can run and it can be pretty fast, and it can be pretty accurate. All right, so this is for the quick demo. As mentioned before, one of the reasons why it's so fast, so reactive is we're using something called Arrow. And the idea of Arrow is that you have this unified memory format where you say, okay, an image is just going to be this continuous array of data. And if you want to read it, just read this, and then it's just going to be this unified. If you say that it's an array of U in 8, it's just going to be this way, and anyone can read it, right? And you don't have to copy the data because the format is just going to be the same for everyone. And if we take this abstraction, basically you can come from Python, Panda, PyTorch, OpenCV, and just read this data without having to do any copy. And this gives you a lot of performance boost compared to something where you have to do copying. So for example, if you use ROS2, basically you have the memory message format is protobuf, which means that the memory format might be different from OpenCV or NumPy or PyTorch, meaning that you will need to do a memory copying. And one of the things that is costly about memory copying is that you have to do a memory allocation. And if you're doing a lot of memory allocation, it can really eat up the performance. And so this is why you have zero copy in Dora. And it's very performant on big data like images or depth camera data. And it's even more performant when you can do zero copy on GPU, which is something that we did very recently, which is actually not very complicated. What you do is just you pass the GPU pointers from one process to another, and Arrow gives you this abstraction that say, okay, this is a GPU pointer. This is how you pass it from one process to another. And this also brings you like a 10, 20 time boost compared to just CPU because you don't have to do the CPU to GPU copying. and CPU to GPU copying again, right? And hopefully we can do this on multiple languages, right? So you could have like Python that is dropping data on the GPU, and then you can have a Rust that is reading the GPU buffer data without copying, right? Which is something that's not actually very easy to do, but hopefully with Dora we can do it. And hopefully we can do this on any type of GPU, right? Okay. Now, I have one last cool trick on my sleeves. I hope I have time, but yeah, there you go. We can also do on distributed, right? So the YAML graph doesn't work just on my computer. It also works on distributed system. Because, for example, in this case, I have a 1580 computer, which is pretty expensive in many ways. And at some point, basically, there's a good reason. All right, let's not show this. There's good reason to believe that if you want to do robotics, you will probably need a lot of gigabyte of graphic RAM, which is probably never going to fit in computers, right? You probably want to have 100 billion parameters AI models. And so we really worked really hard to have distributed data flow, and we do this with Zeno. And so if you just arrive, Zeno just gave a talk right before, and so hopefully we can do a cool demo about it. And the idea is that basically what I should do with Dora is just connect my daemon to a cloud instance. And so in this case, it's AWS. And then what I can say is just, I don't know if it's going to work. Yeah, I'm not sure. All right. I'm sorry, it's going to be a bit small. But basically what I can say is, OK, now I'm in a cloud instance. And instead of running on my computer, you're going to start and you're going to send multiple commands on multiple daemons, one in the cloud and one in my computer. And we're going to try to do the demo again. So if I say QuenVR remote, so I have a new graph called QuenVR remote. And in this graph, I have some specification of, OK, you're going to use the machine GPU, right, for example, which is the GPU instance. And basically, the node, instead of being spawned on my computer, is going to be spawned on the cloud, all right? So let's try if it works. Maybe it doesn't work. Sometimes it doesn't work because of the network or a lot of things. But normally, it should work. So now, for example, all this data is actually coming from the cloud. And so now it's telling me that everything is ready. So same demo, but if I look at my computer, and if I type NVIDIA SME, I don't have any GPU workload on my own computer, right? So normally, it shouldn't be able to pick up the sausage, shouldn't be able to do anything, right? And yet, if I say, make a hot dog, please. Come on. All right, that's fine. Grab the sausage, please. All right, so as always, when I try to do a demo in real time, never works. So, OK. All right, there you go. So it's a bit slow. All right. Yeah, so he tried a couple of times. Grab the sausage again, please. So it's a bit slow, and the reason why it's slow is that there's a lot of, come on. All right, let's try again. Okay. All right, grab the sausage, please. All right, there you go. So it's still running, and so this is running on the cloud, right? But we see that it's still slow, right? And the reason why it's still slow is that if we look at the system monitoring, I'm pushing about 1.7 megabyte of data to the cloud because all the data is not compressed. It's just raw data going to the cloud, right? Thankfully, we have a good Wi-Fi here. Otherwise, this would have not worked. But one way to fix this issue is to do compression, right? So compression is what you do when you do WhatsApp calling, if you use any type of streaming like Netflix or YouTube. And this is how basically you're still able to have good performance. And because we are Rust for robotics, the good thing is that there's really good encoding and decoding project written in Rust. One of them called Rave1E. And it claims to be the fastest. It's actually not, but it's pretty fast encoders. And so if you use this encoder, basically what you can do is software encoding of the data, both images and depths, up to 12 bits. And 12 bits is about 4 meters, which is about enough to do this demo. And then you can do the decoding online. And then you can use Zeno to have something very fast. One of the things that is pretty cool with Dora is that you do the encoding and decoding once, and then once you're in the cloud, you can have multiple. For example, you can have SAM2 and the VLM use the same data used through shared memory instead of decoding multiple time or encoding multiple time from the local instance. And then you can do this, right? So let's try to run this again using compression. So instead of using the QuenVL remote that I just showed you, have another one, exact same one, except that we have Drive1E running locally on my computer, and Dave1D, which is standing for like AV decompression running on the cloud, right? All right, so let's try to run this. So now everything is running. All right, not yet. Everything is going to be running about now. And now if we look at the data that is being pushed, we're only pushing about 600, right? So we divided it by, I don't know, 10, 5 times. And the cool thing is when we reduce the bandwidth, we also allow to do computing on 5G network, which is probably what you want to do to have a very reliable way to run your robots anywhere, right? So yeah, and so we're doing both lossy compression of image and depth, right? Okay. So let's try to see if I'm not bullshitting you. So if I do make a hot dog, please. So, so he's still like struggling a little bit, but all right, let's try again. Let's try again. All right. All right. There you go. Can you make a hot dog, please? So you should feel like it's a little bit faster. And all right, there you go. So it's not that bad of a demo, but basically everything. yeah. So yeah, so everything runs, and yeah, we're using only 600 kilobytes of data, which is good. And knowing that this is still a POC, there's a lot of improvement we want to make. But the idea is that you would be able to run it anywhere. You can run it on the field just with 5G data, and everything would work well. All right, this is the end of my talk. I think I'm past time. All right, but yeah, if you have any question, feel free to reach out. Yeah.
Thanks for the talk. That was great. You mentioned that most of your communication, or the principle behind your communication, uses zero copy where possible.
Yes.
How do you handle stuff like, for example, JAGs where you have immutable areas and you want to share that? Do you natively handle that, or do you have to explicitly declare, like, this is GPU to GPU communication, but you shouldn't change any of the underlying data?
Yes, so it's read-only. So we pass the feature flag of read-only because it's you can't do, and so you have to copy on write. Yeah, but it's read-only, zero copy.
So so also if I, for example, transfer torch data, it's always read-only.
Yes. Yeah.
Okay. Cool. Thanks.
Yeah.
I think we actually on a tight schedule. I think thanks again, Hakia, for the talk. And the next speaker is okay, right? Yeah. Okay. So thank you.
Yeah, nice.
Test.
All right. Thanks so much. Yeah, thanks for the introduction. I'm going to talk about Sophos-RS. I'm Hauke Trusted, and I'm working at Space NG. See, how do I? Okay, so let me talk a little bit of about myself, what I've been up to over the last 4 years. 4 years ago, I joined the startup, the farm startup, farm robotics startup, Farm NG. And back then, it was a pretty small startup, like just a couple of people. And we didn't really have any venture funding back then, so we did a lot of contracting. And one of the contracting we did with a space company. So what I've actually been working on over the last 4 years is a vision navigation solution for a lunar lander. This is for the lunar mission by Firefly Aerospace, which is part, and the customer is NASA, as part of the NASA commercial lunar payload systems. And as I said, we were responsible for the vision navigation, basically positioning based on camera images. Yeah, the lander landed on the moon on March 2nd this year. Okay, thank you. All right. Okay, now to something completely different. Back in the days, in 2011, I wrote a library called a C++ library called Sophos. It's a library to represent rotation and translations in 2D and 3D as Lie groups. It is based on Eigen, but adds Lie groups to it, and it's inspired by the library called Toon. Maybe some people remember that library, and it's used often in conjunction with nonlinear squares libraries like Series, GTO, and so on. And that library is used in the robotics, computer vision, AR/VR community, Google, Meta, Valve, ROS, SLAM libraries, and so on. Well, we all know Rust is great, so I'm really excited about Rust. So I ported, and I basically ported Sophos to Rust. So that was the main motivation, mostly as a hobby project, but also used starting to use a little bit in Farm NG. So the core motivation is to have Lie groups, but also adding a few more geometric concepts and tools for computer vision robotics, like camera models, numerical optimization, and so on. So the current status of the library is, well, I'm ready to share and get feedback. The API is still unstable in a way that I might delete whole features or might swap out fundamental dependencies. But I'm really aiming for correctness and good test coverage. The overview of the library, so it supports, so it's like a core part of it for different linear algebra, aspects based on in algebra. There as Lie groups. There's tensor and images based on ND array and algebra. There are sensor models, sparse nonlinear squares optimization, which I will talk a little bit more later, and also simple renderer viewer. Okay, what are Lie groups? A Lie group is a group of m by m invertible matrices. So basically, you have a group operation, so you can multiply 2 elements of the group, and you get another element of the group. But they're also smooth manifolds. So what does it mean? So like a good example are rotation matrices. In order to combine 2 rotations, you multiply them and get a new rotation. But the manifold aspect really is that there's an exponential map. And the whole idea is like A 3D rotation matrix has 9 parameters. You can also have a quaternion, which has 4. But if you want to have a minimal parameterization, you know, which is only 3 degrees of freedom, they can be really handy, especially for numerical optimization. So there's the so-called aspect of a concept of an exponential map, where you take a tangent vector and you map it to an element of the manifold or of the Lie group, and then there's also an inverse. So the example for 3D rotation is that you take a rotation vector, which can be understood as axis times angle or angular velocities, and you and that exponential map maps it to 3D rotation matrices. The libraries support the following structures at the moment, like 2D rotation, 3D rotation, 2D and 3D isometries, rotation translations, which are also called special Euclidean group, SE2 and SE3. And recently had some fun also adding the Galilean group 3 of space-time transformations. And I plan to add more in the future. Okay, so how is it implemented? The core concept really is to make use of generics, and there's a generic, well, there's actually a generic type called Lie group. And if you want to implement something concrete like 3D rotations, you basically instantiate the Lie group and you plug in the rotation implementation as one of the parameters. The other set of parameters are, the degrees of freedom, like 3 for rotations, parameters 4, in this case, it's represented by a unit quaternion. The dimensions 3, you map 3D points using a rotation, and then the another 3 is for the matrix dimension, if you represent it as a matrix. You see a lot of parameters here, and the reason is that generics are still limited in Rust compared to C++. So it's not really easy or pretty much impossible to deduce these parameters from the rotation 3 input type. So you kind of need to list them manually here. So one of the core motivation having this one single type instead of multiple distinct type, this Lie group type, is that you can basically write tests, unit tests against the Lie group, and then it covers all the different implementations. And basically, mathematical properties map very nicely to property tests. So, the property is, if you take the logarithm of an element and then the exponential, you get the same element out, holds for all Lie groups. So you write this test once, right? And then it applies to all your groups. And then the other type of tests, this is one for a derivation of the exponential map. So that's really cool because you implement a new type, you add more test coverage, but then you improve the test coverage for all the implementations, not that one. I want to talk a little bit about another aspect which is kind of fits into the system. It's called the affine group template or semi-direct product. You can take any Lie group M by M and plug it into this form where you augment it by a Euclidean vector and zeros on the bottom and the 1, and you get a new Lie group out, right? So this way you turn rotations into isometries. You can turn similarity transforms. Basically you can add translation to your Lie group. And it's done in a way that this group, the affine group template, is implemented once, and then the isometry is just an instantiation of the Lie group with a template. Well, do we get everything for free? No, not really. So we still need to implement the so-called Lie factor group implementation trait for the rotation 3, because there are some some things you need to know. How to fill out, for instance, some terms in an adjoint. Okay. Let's see. So the library supports different derivatives. So we can, oh, what did I do here? Okay. So we can support curves, like, these are functions which take in a scalar. We can support scalar maps, which is a function which returns a scalar, vector maps, a function which returns a vector, and matrix valued maps, which returns a matrix. And it supports numerical differentiation as well as auto differentiation using dual numbers. So basically, so this is kind of, like, for instance, this is a projection function. You take a 3 vector and return a 2 vector, and we divide by z, that's kind of how you would do the auto differentiation on that term. See. So the whole design is that all groups and all other mathematical functions are not implemented against concrete types, but this more abstract type S vector and then the dimension. So this example here, we have the exponential map of 3 rotations, the implementation. And if we do that, we get a bunch of things, right? So this S vector R can be a dual vector R, so we get auto differentiation for free. And it also can represent batch vectors. So you can have a vector of or batch types, sorry. So basically where every scalar is actually a tuple, right? And then you can basically perform SIMD optimizations on it. So for instance, if you want to have a use case where you not map a single rotation or like a single exponential rotation, but 8, you can basically instantiate the batch vector type, and it should be more efficient. So like one thing you see in the code here, you have the select, which is basically an if condition, but it works for batch types. Okay. So this is just an overview, of the different types, like scalar, vector, matrix, real type, dual type, and then if we put in the SIMD feature, which is currently just a nightly, we also get all the batch types as well. How am I doing on time?
You have 10 minutes.
Okay, cool. So let's move on to the next topic. This is just a small niche idea. So the way images and tensors are represented is the following. So as for instance was said in the rerun talk, I mean, it's really important to kind of embrace the ecosystem and use what's there, right? So we know ND arrays are really good for like dynamic tensors, and algebra is really good for static types, right? So the idea is to have a type which is a dynamic tensor of static tensors. So basically, static tensors can be of rank 0, 1, or 2, scalar, vector, or matrix. And the scalar can be, like primitive, U8, U16, F32, or even a batch type, right? And then you have an ND array of that, right? So if you want to represent a U8 RGBD image, you would have a tensor view rank 2. So the dynamic rank is 2, width and height. And you have 3 rows per pixel, like, 3 elements per pixel. So 3 rows, 1 column, so it's like static rank is 1, right? And of course, you can also just, represent like a standard dynamic tensor, right? Like a 4D tensor. Okay. Yeah. So one thing okay, let's talk about sparse nonlinear optimization. So this is a very common problem you need to solve. You have a cost function which has the following form. You have a sum over some square cost terms. And this is kind of really important for a lot of applications in like classic computer vision and you know, like and robotics, like camera calibration, binary adjustment, post-graph optimization, right? And like, you know, the big libraries out there in C++, the series, GTO, GTSM, and so on, right? There's something similar in Rust, which is called argmin, but this is not a sparse library, so it can be really slow. Sophos RS supports sparse linear optimization. So in this example, you kind of have a variable family that could be like, for instance, a list of 3D points, and you implement the cost function, and you have multiple variable families. For instance, in bundle adjustment, one family would be points, the other one would be you know, poses or isometries, and then you have this free function which is optimized nonlinear squares, and so that's kind of the interface. Let me see. Oh, what am I doing? How do I get rid of that? Okay. Didn't know that was on the screen. Okay, that's much better. All right. Cool. So the implementation is the following. It uses Lebenberg-Marquardt. It's like, you know, a Gauss-Newton variant. That's kind of the most standard way of implementing it. It uses like that's for the nonlinear squares part. The direct solver for the normal equation for sparse Cholesky uses the excellent FairCrate. It also supports equality constraints, and it supports multithreading using the RainCrate. Okay. So this is a toy example for post-graph optimization. I implemented, basically you have a loop, like a robot moves around, and then there's kind of an error in the knowledge of the positioning, and you optimize that loop to distribute the error over the graph. Yeah, I think I kind of go over this pretty quickly. So for like even a pretty big graph, there's 2,500 poses that only took like 50 milliseconds when single threaded. Okay, so lots of things are happening. So when I worked on that in 2024 last year, two other crates popped up working on exactly the same topic, which is really exciting, right? Because it kind of shows that there's a lot of happening in that space. So one is the Effect RS crate by Ethan Potokar and others, and the other one is Tidy Solver by Powie, Lin and others. And wouldn't it be great if there would be like a performance benchmark between the crates, right? I thought so, and I was wondering, whether I should write one, but actually looked at the internet, and the Fact RS crate, they just published a benchmark 3 weeks ago, which also includes Sophos RS, and you can see here the relative performance, also showing the heavyweight C++ implementation, GTSM and series. And as you can see, Factor S is doing really great, right? Sophos is also in the race. So the race is on. So this is really helpful because now you can understand where things you can improve, right? Just looking at the other open source implementation, we're really doing well. I think it's really helpful to have that. And if you want to know more about this, there is a post outside from the authors of FactRS, and they probably can tell you more about that benchmark. Let's see. So just one quick topic. So this Sophos RS also includes a simple view on off-screen renderer. which has a similar, it's not using rerun, but it has a similar stack to rerun. It's using EasyUI and WGPU. It's pretty small and lightweight, so it supports 2D primitives, 3D primitives. One of the core concepts is that everything is off-screen rendering. So if you want to, that means you can also use it for like simple camera simulation, right? Because everything you show on the screen, you can also get in a texture and save to disk. And one of the features which it has, it supports camera distortion, which uses a multi-render path approach to do so. Okay. All right. Wrapping up. So here's just a few ideas of things I want to kind of add to the library. Maybe I'm not going to go through it one by one, but leave it open and see whether there's some questions. All right.
Any questions? No? Any questions online, maybe? All right. If no, then we go into the panel session. But thank you.
Thank you.
Can all the in-person speakers come up stage?
So,
Yeah.
I think for today's sessions, we have two panel discussion. So the first panel discussion is gonna come out among the industrial speaker. So I'm gonna invite Jeremy, and I'm gonna invite Guillaume, and also I'm gonna invite Hockey also on the stage. And also we have another guest from Matic Robotics. I'm gonna invite Rachel Fu from Matic Robotics also on the stage. So for this session, Haishen will be the chair and moderator. So we're gonna discuss some questions, and let's see how the discussion is going.
Yes, we should sit down, right?
Yeah.
Cool. All right. Should I sit on your position? I think it's.
I think you can
Huh?
sit in here.
Oh, can I sit in? Okay. Oh, that's good.
Yeah.
Should we pass the mic?
Yeah.
No, we can't.
Oh, we can't?
Yeah, it's too short.
By the way, Yang, I don't know if you saw my message. Just to double check.
Oops.
Hi. Shall we start?
Yeah.
Hi. Did we do the introduction? Or yeah. Okay. We can introduce.
Yeah.
So Cooper Robotics, which is kind of the robotic engine written in Rust, a space engine that's especially on nonlinear solver. Jeremy from Rerun about utilization, and I forgot your name. Yeah. Rachel on many group robotics, right? Yeah. Could you just say a few words about many robotics?
So we are a
That's okay.
Hi, my name is Rachel. I am a perception engineer from the Matic Robotics company, and we make home robots. And we currently have like over 1,000 robots in real customers' homes, and 95% of our code base is actually written in Rust.
Great, thank you so much. All right, so my first question is gonna be about how, like, there's many people in the field, in the audience today, which is about embedded robotics, right? I think it's kind of like the underlying
theme about robotics. And so how do you feel Rust fits into embedded system nowadays today? Do you think there's still drawbacks and still issues? Do you think that moving forward is the go-to solution for embedded system? What do you guys think?
Okay, yeah, I can start. Like, so the robotics embedded system is starting pretty well, right? You have like all those like traits. I don't know. So for people who are not familiar with that, there is like kind of standard traits for actually integrating Rust into like small systems. So let's say like a microcontroller and so on. And you have like implementations of like in the industry for like specific boards, right? Like you can have the one for Raspberry Pi. I think there are two, I think, for Raspberry Pi and so on, right? So for example, on the Copper side, we are looking into doing that, into actually going into what we call like no STD on Rust. So basically, really removing all the standard library that has like allocations or all the dynamicity of the standard library to be adapted to like the really embedded systems. So it's tricky, right? Because like as usual, when you have like those like boards, you have like it's like a zoo of boards, like big ones, small ones, like a bunch of like various like IOs and a lot of like partners you need to actually push through to actually implement those traits on the embedded side. So my experience with it is that it's a kind of midway. So some of things work, like simpler stuff works very well. If you go like to a Raspberry Pi, it's like or like a I don't know like a Pi Zero or those kind of like small systems. And very common ones, it's very easy to do. But if you start to have like I don't know like other like manufacturers, ARM and so on, they can be really hard to actually set up. So that's really my experience there. So if you have like something that you know you can aim at, you have other examples of other people doing things on the embedded side, it's pretty easy. If it is not your for a bad trip with Rust embedded. I don't know who else has some experience. You must have some. 95% of your code base.
Yeah. I mean, like from our experience, like we don't really put a limit on what you can do with Rust because like we started from SLAM. We start like about 5 years ago, we started like rewriting our SLAM system in Rust. And then later we just started because like it actually works so well. Like I think we haven't had like a seg fault for like 4 years, 5 years, ever since we moved to Rust. And then we just start moving other parts of our code stack and also into Rust and then planning and now our quality controls, well, I mean, we still do our training in PyTorch, but like we don't put like we also like just pack it with TensorRT and then also like just use Rust bindings. Basically, like I feel like we don't really put like a limit on like what you can do with Rust. It's like whatever you want to do, and you want to like put it on your robot, and you want it to be reliable and have good performance. Just do it in Rust. Yeah, like if I think we currently have like about like 2,000 to 3,000 external crates that we use, and if you can't find something that's good enough, then just write your own. So yeah.
It's just real quick. I mean, yeah, on the specifically embedded Rust side, right? This is probably one of the places that rerun, right? I talk about like use rerun like everywhere, and if you get into that like no STD ultra embedded context, right? There is a higher bar there. We haven't taken that investment. We've thought a little bit about like what we might have to do to get there, but I would say that this is certainly a point of friction within that like Rust portability story, and I'd love to see progress on that. But I think even like in a rerun story, right, we look at something like other frameworks to just really focus on that minimal, like get the data out of the system, and then for rerun add the data transformation visualization bindings after you get off the embedded system, sort of as the approach to dealing with a little miniature Rust core. I would be hopeful like Zeno might solve that problem for you for us to get stuff into another context where we could work with it.
So I think you're totally right, and I think in general, you mentioned it as well. Rust, if something already exists, I think it's really good, and then Rust works really well. STD works really well. No, STD is kind of like a wired environment where the thing's missing, and it's kind of harder to use. Do you feel like there's any package that is critical for robotics that is still missing, or that you wish that you would see happen? Or like something that you, like for example, for me, I feel like Slam is something where I would wish there was a very good like Rust-based solution for Slam. But yeah, do you have anything that you wish would happen? Yeah.
Yeah, so there have been all like requests like on the core side, especially when people coming from Rust, right? They expect like those like big package. I don't remember the name, like of all the routing thing, probably linked to Slam and so on. So there are a lot of like low-level things for Rust, for robotics. Like we've seen linear algebra and so on, all those kinds of low layers, right? But we don't have like big libraries that I would love to have available for like high-level robotics, but really like routing and planning and those kind of things where we could use them through Rust, Dora, and Copper, for example. That would be amazing. Hopefully, if somebody does that, makes a library and don't like link it too much to one of those frameworks, we can use them. But yeah, that's really what we saw. One request was, for example, like a transform chain, for example, for Copper. We implemented that recently. So all those kind of high-level robotics miss a little bit. But you must be implemented a bunch of them, right?
There's plenty. I think I wish I implemented myself. I think, for example, like one of the things still missing, in my opinion, is maybe the inference engine in Rust. So there's there's Burn, there's Candle, but it's still basically the performance is not exactly there yet, and there's a lot of like things that is not ported yet on Rust, and I feel like this is one of the biggest gaps, right? And especially when you see that AI model is taking off, and it's kind of like one of those big things. So you mentioned also TensorRT and how you have to export it, and then you probably have CFFI bindings to take like a runtime, and it's not great, right, to have this runtime thing, or yeah.
It's pretty good.
It's really good,
Yeah.
yeah. But I mean, yeah.
Yeah, so basically what we do is like we also, cause like all our inference actually run on bots. Like our robot can work without internet connection actually, because like we want the data to stay on the device. So what we have to do, like we don't put any code or anything on the bot. So what we have to do is like we have to train the model, and then we have to inference the bot, like, and all of that is written in Rust. We have implemented like our own crate that does that. So it basically turns like our like design into like a static graph, and then we just like load in like the binaries that we have. Yeah, so as for like what crate that we want, like that's still missing, I think a lot of them are like actually like specific. It's like, for example, like if you have like a specific hardware or firmware and you want to like bridge the gap. So I think we also like written a bunch of crate that helps like, for example, helps efficiently save and load our map layers. And we actually open source that crate. So like if anyone has like similar need in the future, they can just use it. Yeah.
Yeah, I think I mean, sort of an interesting thing I'm observing sort of right at this phase that we're in right now is a tendency for multiple the thing doesn't exist, and then, multiple companies all re-implement, pieces of that thing themselves, or it takes a little bit of extra burden to go that extra step to, I would make this a reusable crate that other people can build on top of. And I think this is a little bit of just things that are like shaking out right now. Like you mentioned the transform graph, sort of like the Ross TF2 transform sort of thing, right? This I think has been one of like the biggest stumbling blocks to getting Rust for Ross like brought up is, we got the message passing and other things. But do you have like native like Ross transform? We don't have like Ross transforms. Like and then like that's like one of like the core things that sort of needs to be there. Rerun will certainly be doing either this ourselves or trying to, find someone to provide this. So this is probably a good opportunity to, talk to this group. It's like who is doing like the most authoritative, like ROS style, TF2 compatible. I mean, really, like you want like a mathematically identical, right? If you want to sort of like match the expectations of what's happening in ROS, then there's just a lot of like little details to get right that are going to get missed if everybody's doing inconsistent, but intention, like trying to do the same thing, but with slight differences in implementation.
Okay. Just wanted to say, like, Young actually ported TF2 to Copper just like a few days ago.
Fantastic.
Yes.
Yeah, I also want to mention another aspect. So if you actually look into
It's okay.
So if you look into a low-level linear algebra, the libraries out there which are really well and doing it really well in C++, like Cirrus and Eigen, they make heavy use of templates, and they're really useful, like really powerful. You can do a lot of things with it. In Rust, for instance, you can't do some very simple things, right? If you stack a 2D vector with a 2D vector and you want to know that the dimension is 4, 2 plus 2 is 4, you can't do that yet as a const generics, right? So in the Rust language, const generics, I mean, the folks are working on const generics expression to get it to work, but it's still far out. I mean, I think they're working on a minimal design at the moment, which would not yet, allow for this kind of, addition. But, I think that would allow for some kind of traits. So you can kind of query from another generic what the dimension would be. So there's definitely also, I think there's actually a fundamental feature lacking in the Rust language, which would, help a lot that whole level. Libraries.
Thank you so much. So last question, which is kind of, we talked about the good thing with Rust, the bad thing with Rust, I think. And so it's more like an opening question for the public and for the audience, which is basically, how do you see the Rust for robotics ecosystem grow in the next 5 years? What will be the integration? Like, for example, for me, I talk with a lot of robotics company. I see more and more company like writing everything in Rust from day one, right? Especially the new one. The old one has some legacy C++ and they stay with it. And so do you think that in the future, almost all companies will stay in Rust for robotics? Or do you see a mix yeah, it's kind of like what's your guess? What's your vision on the Rust for robotics for the future? Yeah.
Yeah, so I mean, like it feels a little bit like kind of, for me at least, self-obvious that people will gravitate towards Rust from C++ because already it's really complex to actually build a robot. C++ doesn't help at all, right? And I think that has been identified, and especially when you have like people, like very mathy people and so on, going into C++, yeah, you'll get those kind of like mistakes, and so. You see what I mean? It's almost like gravity. Like everybody's gonna come towards Rust, and you'll see more like all the basically the velocity of people like kind of building robots will go up, and that's gonna lower cost for robots in general. Like you've been into this too, right? So knowing that, right, like people from companies, I think it's gonna be very let's say organic, right? Like all a small team makes small components and start to integrate and so on, and it will bubble up through the industry, and then you'll start to see higher level standards, like we've seen with ROS, for example. ROS is like the basic components and so on. And I think that's what I'm looking for actually for the next couple years to 3 years, like a lot of like those high level libraries and start basically the industry starting to reuse their own work to actually accelerate the robotics on that side. So that's really how I see that for the next few years. And it's going to get quicker than 5 years, I'm sure.
Yeah, I mean, I think this is something I sort of hit on quite a bit in my talk, but I think that this idea of using Rust specifically in the low level contexts where it really makes sense and you're really getting that value is like sort of where I see like the robotics context. You're moving right like the sensor drivers, things running, specifically on robot places where we are needing to close real-time control loops. Like I think definitely do those things in Rust because that makes sense. And then, again, taking advantage of this like Rust, like this model of taking another language, implementing bindings on top of some Rust core. Like we see this pattern like showing up again and again, and I think much more so in Rust than like you could have done this with like C++ and Python for ages now, but like just not with the same productivity, not with the same velocity that I think we see people sort of deploying that model today with Rust. And so like I think that this vision of you use Rust up to a point, and then at some other point in the stack you switch to Python or you switch to another language that's a little bit more suited to the task, but you build on top of that guarantee that core foundational layer that you're building on top of is Rust, and it is safe and it is performant, and you're not like as inclined to do this like Python, we're going to do a Python native implementation so that we don't have to leave the Python interpreter, it doesn't feel well intentioned at this point when it's so easy to like just drag libraries in and use them from Rust when you need to in another context.
So for me, like from an engineer's perspective, I would say like one big advantage of Rust is like it allows us to when you work in a company, it allows you to like have like very fearless refactoring of other people's code. So for me personally, I've like switched in between like different projects, and like if it wasn't Rust, if it was like C++, it would like take me so much more effort to like start working on other people's code. And also I feel like one of the reasons our company's code base is like the vast majority of our code base is in Rust is like we feel like it's important that we work in a language that's the most comfortable for the team instead of like a language that's most comfortable for each of the team member. Like a lot of our engineers actually have never touched Rust before they join, but like it is like just such a well-organized language, and then people just like pick it up very fast. And then if you do it in a idiomatic way, people's like coding styles are also like very similar to each other. So like the whole code base just looks like very constructed. So I feel like that's also one of the reasons if you work in the industry, you might want to like choose Rust as your language.
I think we're just in time. It's 12. Oh, yeah. I will still have some time. All right, sorry. All right, so I think Oh, okay, so 30 minutes more. Okay. So in that case, I just want to, which was totally prepared. I want to jump back on what you just said, right? Which is like, what have been the experience on onboarding new team members that probably never touched Rust, right? Probably a lot of people in the audience online never touched Rust before, and so what have you had as an experience? Do you have any tips on onboarding new team members? And kind of this board.
Oh, that's a good question for me. I did that several times with several teams. So first, I would like to know actually in the room who actually can read and write Rust. So let's say read Rust. Okay, so it's really almost like let's say 75% Rust speaking audience. So so that's interesting because that's for you guys and also for the others on the receiving end, right? So one thing I noticed is like if usually in robotics people know C++, and when you know C++, kind of like Rust makes sense for a lot of like core concepts, right? So it doesn't shock people when you talk about like, who owns what what's a reference ownership type of system? When you write C++ correctly, you need to worry about this, right? And so for them, it's more like a tool that extends their own productivity. So what I do usually I use Rustlings. I don't know if you know this one. And because Rustlings is at the right temperature for somebody that knows C++ and just wants to know, okay, what are the little, like, I don't know, syntactic or like a little tricks you need to learn with Rust. And usually for like a team, I did that, for example, with 5 people, and within a week, they are actually already productive on their code base. So to be clear, right, we are talking about robotics also, right? It's not like you're writing an operating system, like in a week, no. Somebody that is like very familiar even with C, let's say on the Linux kernel to do that in Rust, they won't be able to do it because you need to learn like a bunch of like very low level things. But for robotics, it's very high level, right? You go through like functional like features of Rust. It talks like so much to people that know Python and knows robotics and so on and math, and you drag them through that, and usually within a week they are actually productive, and you feel comfortable actually having them writing code more than in C++ because you don't have to wait for a gotcha in the middle of the code base. So yeah, generally, and they are like delighted after a week. They love actually that language.
All right, that's maybe half an answer to the question, but I think what really helps, what I really like is the feature of Rust is that it comes with all the features included, right? Package manager, there's one package manager. There's no discussion about it, which package manager to use, right? Same with integration in, like VS Code, right? It basically all comes like included in the language. In C++, if you have a library, which does exactly what you want, it can be sometimes impossible to integrate into your stack, right? Whereas in Rust, you just just add it to your cargo tunnel and it just works. So I mean, I think that's really great.
Yeah, so I mean, yeah, when it comes to like ramping new employees, up on using Rust, like when I the first Rust code that I wrote was during the interview process for Rerun. I made a take-home code test, and it was in Rust, and I hadn't even I had not written. I'd maybe done like the Rust Hello World like application like 2 years before that. Like I knew almost nothing. They said, "Would you be willing to do the code test in Rust?" And I was like, "Well, like as long as you give me like a little bit more time, yeah, sure, why not? Well, like either this will work or it won't." And like I was shocked at just how well it did work. And this was 3 years ago, and I feel like Rust Analyzer has like even continued to get better in that time. But like as someone that familiar with C++ and Python, and like I'd read about Rust and knew about the concepts of Rust, VS Code and Rust Analyzer was like enough to like make it through a coding test and get hired at a company that like is a Rust first company that only works in Rust. Right? Like now, by no means was I like fully proficient with Rust on day one, but I do think that having Rust Analyzer, having good compiler error messages, like people, I think back, I don't know, 4 or 5 years ago, and people really talked about like Rust being hard and scary and like and challenging to get into, and that like has not actually been my experience at this point at all, just because like the state of the tooling support and the documentation support is all quite good. And so I think that like in some sense, like throwing people in the deep end of like a functioning Rust code base is one of like the fastest ways for people to learn, and sort of trusting, the safety of the compiler, this fearlessly refactoring like big pieces of the code base that you wouldn't dare touch in another language, like does give people an opportunity to struggle a bit, but struggle with like very good support along the way. And I guess I'll just add into that, like because of that, like having good unit tests is always like just so critical to being able to do these things. Like you can get pretty far with like the code compiles, and if the code compiles, it's probably going to work, but like the Rust unit test framework in general sort of like makes going that one extra step like not all that challenging either. And again, there's one unit test framework that you choose. It works with cargo. It's just like it's having everything included there and decided for you, again, makes this a very approachable process for new people coming into Rust in the context of a working code base.
Yeah, I totally agree. So for me, I was pointed to the Rust book 3 days before my first day. And then I actually started like writing code in Rust the first day of my work, and it just works out. So I feel like it definitely helps to have like a huge code base that's written in Rust, and then for new people, they can have like smaller project that's based on top of that. And also, I personally feel like Rust is actually a language that totally makes sense. And when I just started on it, it feels to me more like it's kind of like C++ or any other language, but it also forces you to build like a good habit. So yeah, so theoretically, like all it does is to like force you to pay attention to things that you probably didn't pay attention to before. Yeah.
Right, so I have one question from the audience, from the Zoom audience. And I think it's an interesting question. It's kind of a divisive question, which is, what do you guys think about async? And should it be part of STD, basically? Yeah. Which is kind of I can tell what type of Rust people you are just based on this question, I think.
Give some
You have
context.
Oh yeah, yes. Oh yeah. So for people who don't know, async is basically asynchronous Rust. And so it's what you need to use to do basically concurrent calling. That's what you're using web basically, right? But the thing is, like, it's almost an entire different thing as Rust insync, right? Because you have a lot of like guarantee issues that you can't have in async. And so yeah, what do you guys think about async?
I can try on this one. So you know that Copper shied away from asynchronous things, right? So first, like I'd like to be sure that we are in the bounds of robotics, right? And like you said, like usually async. Why do we want async in a language first, right? Like because otherwise people just throw that at everything, right? Usually it's on highly concurrent contention on the machine IO bound systems, right? So imagine like a web system where you have like 10,000 users running on a machine, and you have requests coming in, and you need to absolutely burn through a lot to actually have the most bandwidth out of your system. Okay, this is made for this. This is not made for a robot. Like a robot is not about bandwidth; it's more about latency, right? So first, like to kind of at least on the robot itself, I don't think it's a good idea, right? Now there is another layer of controversy on the async thing on Rust, is that it's a kind of a viral property. So basically, once you start to have one part of your code base written with async, you feel forced by the nature of what you need to implement to be able to be async compatible. Basically, your entire code base starts to basically get like zombies. You need to go through your entire code base and port it to be async, right? So it's basically most of the time. I don't think they have a solution today. Most of the time, it's an all or nothing choice. So suddenly it becomes really like invasive in your code base, and it adds a lot of complexity because you can imagine like Rust is all about like, okay, ownership of pieces of memory and so on. So when you have a highly asynchronous system, yeah, you need to pin the memory to be sure that it is not moving and so on when you have callbacks. And so it adds like a huge layer of complexity on top of your Rust code base. It's like it's almost Rust is fighting you a little bit with the asynchronous side, which sounds absurd because Rust is actually really good at actually concurrent systems, right? So that's a bit my opinion. I don't touch that with like a 10 football.
No opinions? Okay, yeah, great. I mean, I think rerun, our experience matches that almost exactly. The knowledgeable Rust engineers at the company fought introducing async anywhere into the code base for the longest time because of all of the challenges that it introduces, and then we got to a point where there were some key libraries that we wanted to use that that are async, and now async is the tendrils are reaching further and further across the code base, and it's not great, right? I definitely think async needs to be better for async Rust to like really be a thing that I would like recommend that people use as opposed to like reluctantly agree to use when you need it for something. And I do think that this, one of the biggest challenges, yeah, with async is very much this like this all or nothing thing. And you see very few like a model of like a library that's like, oh, like async as a feature flag that you turn on, like isn't a thing that I've seen executed well. I've seen, I think, attempts to to do this in some regards, but like there's a lot of code duplication and a lot of like boilerplate patterns, and you can macro your way out of it like sometimes, but it feels less and less like the beautiful Rust that you enjoyed working with. And so my sentiment is, yeah, it's nice to have it there when you need it, but it's definitely not like really ready. And I think the only way we get there is it becoming like a more core part of the language somehow, but I don't really know what that solution looks like other than this sort of, yeah, this belief that like it needs to be there. It also still needs to very much be something that like is opt-in, opt-outable in some fashion.
I mean, our robots has like very complicated hardware, so like different motors and different parts. So we kind of have to use async for the robot performance. We have like modules like split like everywhere across our code base. And that actually like greatly helps with the performance of our robot. So I would say like at least for us, like async is like necessary and good, but like I definitely understand like other people maybe like they don't want to use it, but like yeah.
Just lean it. That's
So if I may, because it's good to have a little bit of controversy, I disagree with the comment on async. I don't know to which extent you have used async.
Which is the guy
Sorry?
who from there, which is the follow. And so like async is very important.
So
Angelo, could you try to speak?
Yeah, can you hear me? Hello? Can you hear me?
Let's test. No, 1 second.
Yeah.
Your system seems shut down.
Microphone of the laptop here.
Yeah, we can.
I can write the comment for now. As long so basically, Angelo don't agree, and async at the language is okay, right? But it's already part of the language, right? The big issue are executors not being part of the language. Yeah. So for example, Tokyo, async Iowa, yeah.
You cannot hear me, can you?
As well for embedded, right? I heard a lot of people like I never worked with Embassy, but I heard a lot of people having a lot of trouble with Embassy as well. Being aced, kind of like one of the reasons being that it's I don't know. So
Can you try to like use the microphone with the speaker? Let's try that. Could have some echo.
Okay. 1, 2, 3. Could you speak, Angelo?
Yeah, I'm talking. Can you hear me?
Right. Yeah, I think we can hear you.
Okay, good. Okay, so I was curious to know that because I cannot see the name, the gentleman that was discouraging the use of async, at which scale it has used it. Because I think per se, the problem is not async in Rust. There are, from my perspective, one challenge that you have to understand, which is you shouldn't mix sync and async. And I think that is in some languages, and if you understand that once you get in the async world, and once you use future, you are in monadic world, and once you are in monads, you should never get out of it, right? But I think this is something you have to embrace one way or another. Then you have to come back to reality, and if you're using async, then obviously it's a little bit more challenging to cross the FFI boundaries, okay? But it can be done. In our experience, the biggest challenge is not so much async or even the limitation that there were up to some point ago with closures and lambda and so on and so forth, and traits which now have been resolved by the latest edition of the language. But it's more the fact that if you write async, you're writing async for Tokyo or STD. because in reality, those frameworks have very different behavior, different performance that needs to be tuned, and you can't easily switch from one to the other. I mean, we had selected, for instance, async STD, and eventually had to move to Tokyo because of ecosystem. And there was lots of fine tuning and lots of, let's say, adjusting here and there to match a model that weren't exactly the same. And so from my perspective, the biggest issue that I have today with async is the fact that the executor framework is not part of the standard library. And
Yeah, no, I don't have anything against async as a whole, right? I was talking about like on robot on and with an existing code base, right? Like often when you have, I don't know, maybe we have like thousands of crates, like we introduce with Copper. Like if we were to touch one and we go to the thing where it starts to port your entire code base to async, it's not possible. But I agree with you, right? There is like something fundamental about async. It's not really about Rust. It's more about the fundamental way of like the impedance mismatch between your synchronous code and your asynchronous code. That is actually the root cause of this nightmare.
Right, so it's 12:20. I think are we on time? Or yeah. All right. So thanks everyone for coming today, and we'll see you this afternoon with more talks, especially on the academic side.